In the vast darkness of space, orbits one small world that we call home. But beyond our sun lie trillions of stars, and orbiting those stars are worlds beyond imagination. Some scorching hot, some frozen solid, and even some that might harbor life. Welcome to Stellar Worlds, where we explore some of the most fascinating planets in the universe. Are you ready? Let's begin. To start today's video, let's take a look at the planet HR 8799c, a directly imaged giant in a young planetary system. TRAPPIST 1D taught us about boundaries, where habitability ends, where conditions become too extreme for life as we know it. We've explored planets detected through transits and radial velocity, planets found by the subtle dimming of starlight or the wobble of their stars. But what if we could actually see a planet directly? Not infer its existence, but photograph it, capture light reflected and emitted from the planet itself. Welcome to HR 8799c, one of the first exoplanets ever directly imaged, a gas giant 7 times the mass of Jupiter, still glowing with the heat of its formation. It orbits a young, massive star along with 3 sibling planets, all visible in telescopes as distinct points of light separated from their star. For the first time, we're not detecting planets indirectly, we're seeing them. Imagine looking at a telescope image and seeing not one star, but a star surrounded by 4 bright points of light, 4 massive planets, each individually visible, each separated from the star's glare by advanced imaging techniques. This is HR 8799, a planetary system we can actually see. HR 8799c, the second planet from the star, orbiting at about 38 Australian dollars, roughly the distance of Pluto from our sun. It's a young world, just 30 million years old, still radiating the heat from its formation. Its surface temperature is around 1,100 Kelvin, hot enough to glow in the infrared, making it visible to our most powerful telescopes. Discovered in November 2008, HR 8799c was one of the first exoplanets to be directly imaged, announced the same day as Fomalhaut b, another directly imaged planet. The announcement marked a watershed moment in exoplanet science. We had finally developed technology sophisticated enough to photograph planets around other stars. HR 8799c is massive, approximately 7 Jupiter masses. It's still contracting from its formation, releasing gravitational energy that heats it to over 800 degrees Celsius. It has an atmosphere rich with water vapor, carbon monoxide, and possibly methane. And it has weather, clouds of silicates and iron condensing and evaporating in an alien climate system. To appreciate HR 8799c's significance, we must understand the challenge of direct imaging. Why is photographing an exoplanet so difficult? And how did astronomers finally succeed? The fundamental problem is contrast. Stars are bright. They generate their own light through nuclear fusion. Planets are dim. They only reflect starlight or, if young and hot, emit modest thermal radiation. A sun-like star is typically 1 billion times brighter than a Jupiter-like planet orbiting it. It's like trying to see a firefly next to a lighthouse. Even if we could handle the brightness contrast, there's angular separation. Planets orbit close to their stars. Even Pluto, at 40 Australian dollars, is just 0.0006 degrees from the Sun as seen from the nearest star system. Resolving this tiny separation requires enormous telescopes or sophisticated techniques. This is why indirect methods, transits, radial velocity, discovered planets first. These techniques detect planets through their effects on stars, dimming during transits, wobbles from gravitational tugs. They don't require separating the planet's light from the star's light. They worked decades before direct imaging became possible. Direct imaging required two key technologies. First, adaptive optics, systems that measure atmospheric turbulence hundreds of times per second and deform telescope mirrors to compensate, sharpening images dramatically. Second, coronagraphs, devices that block starlight while allowing light from nearby objects to pass, creating an artificial eclipse. In 2008, two teams independently targeted HR 8799 with these technologies. Christian Murwa and colleagues used the Gemini North and Keck telescopes in Hawaii, employing adaptive optics and coronagraphs optimized for planet detection. They weren't searching blind. HR 8799 was selected because it's young, massive, and nearby, making planets more detectable. The images revealed 3 planets, designated HR 8799b, C, and D, as distinct points of infrared light at different distances from a star. All 3 were visible simultaneously in the same image. It was unprecedented. A 4th planet, HR 8799e, would be discovered in 2010, closer to the star and fainter. November 13, 2008, the announcement came. 2 teams, working independently on different stars, announced direct imaging of exoplanets on the same day. HR 8799's 3-planet system and Fomalhaut B. After decades of indirect detections, we had finally seen planets around other stars. To understand HR 8799c, we must first understand its cosmic neighborhood, the HR 8799 system, one of the most remarkable planetary systems known. HR 8799 is an A5V star, hotter, more massive, and more luminous than the Sun, located 133.3 light-years away in the constellation Pegasus. It has approximately 1.5 solar masses and shines with about 5 times the Sun's luminosity. Its surface temperature is about 7,430 Kelvin compared to the Sun's 5,778 Kelvin, giving it a white color. HR 8799 is young, just 30 million years old, roughly 1/150th the age of our Sun. This youth is crucial for direct imaging. Young planets are hot from formation, glowing in infrared, making them easier to detect. Older planets cool down and become much fainter. If HR 8799 were as old as the Sun, its planets would be invisible to current technology. HR 8799 has debris disks, belts of dust, and small bodies similar to our asteroid belt and Kuiper belt. Infrared observations detected excess emission from warm dust, indicating the system retains remnants from its formation. The debris disks provide clues about the system's architecture and dynamical history. Orbiting HR 8799 are 4 confirmed giant planets, all significantly more massive than Jupiter. Let's meet them from innermost to outermost. HR 8799e, discovered in 2010, orbits at approximately $14.50 between Saturn and Uranus distance in our solar system, with a period of about 50 years. Its mass is estimated at 7 to 10 Jupiter masses. It's the faintest of the 4, being closest to the star's glare and somewhat cooler than the outer planets. HR 8799d orbits at about $24 with a period of roughly 100 years. Its mass is approximately 10 Jupiter masses. It was one of the 3 planets detected in 2008. Like its siblings, it's a young, hot, massive planet still glowing from formation. HR 8799c, our focus today, orbits at approximately $38 with a period of about 190 years. Its mass is estimated at 7 to 10 Jupiter masses. It's bright in infrared, one of the easiest of the 4 to image, making it ideal for detailed atmospheric studies. HR 8799b, the outermost planet, orbits at approximately $68, well beyond Neptune's orbit, with a period of roughly 460 years. Its mass is about 5 to 7 Jupiter masses. It was the first of the 4 discovered and is the most distant directly imaged planet in the system. The 4 planets orbit with approximate spacing ratios of 1 to 2 to 4 to 8. Each planet is roughly twice as far as the previous one. This spacing suggests possible orbital resonances, though the resonances aren't perfect. The architecture is stable. Computer simulations show the configuration can last billions of years despite the planet's large masses. All 4 planets orbit in nearly the same plane, forming a flat disk-like configuration similar to our solar system's planets. This coplanarity suggests they form from the same protoplanetary disk, a flattened cloud of gas and dust that surrounded the young star. HR 8799c is a massive, young, hot planet unlike anything in our solar system. Let's explore its characteristics in detail. HR 8799c has a mass of approximately 7 to 10 Jupiter masses. The uncertainty reflects the difficulty of measuring mass for directly imaged planets. We see the planet's light, we measure its orbit, but determining mass requires either observing orbital motion over many years or using theoretical models. Current estimates place it at roughly 7 to 8 Jupiter masses. The planet's radius is approximately 1.2 to 1.3 Jupiter radii. Despite being 7 times more massive than Jupiter, it's only 20 to 30% larger in diameter. This seems contradictory, but makes sense. HR 8799c is young and still contracting. It's puffed up by residual heat from formation. As it ages over hundreds of millions of years, it will continue to contract and cool. HR 8799c's effective temperature. The temperature of the photosphere, where thermal emission originates, is approximately 1,000 to 1,100 Kelvin. That's 730 to 830 degrees Celsius, about 1,350 to 1,500 degrees Fahrenheit. It's hot enough that the planet glows visibly in the infrared, though not quite hot enough to emit visible light to our eyes. This heat comes from the planet's ongoing contraction. When HR 8799c formed, whether through core accretion or gravitational collapse, it was much larger and hotter. Over millions of years, it radiates energy into space and contracts, releasing gravitational potential energy that maintains its temperature. It's slowly cooling, but the process takes hundreds of millions of years. HR 8799c orbits at 38 Australian dollars from its star, 38 times Earth's distance from the Sun, or roughly Pluto's distance. At this distance, it receives minimal energy from the star. Stellar heating is negligible compared to the planet's internal heat. The orbital period is approximately 190 Earth years. We've observed about 15% of one orbit since discovery in 2008. The orbit appears nearly circular with low eccentricity, though this is difficult to measure precisely given the short observational baseline. The orbital plane is inclined about 20 to 30 degrees to our line of sight, meaning we see the orbits somewhat tilted rather than edge-on or face-on. The real scientific treasure of HR 8799c is its atmosphere. Because we can see the planet directly, we can analyze its spectrum, the rainbow of light it emits, revealing atmospheric composition in detail impossible for most exoplanets. Multiple facilities have observed HR 8799c spectrum in near-infrared wavelengths. The Keck Observatory, Gemini Observatory, Very Large Telescope, and Palomar Observatory. These observations cover wavelengths from 1 to 5 microns, where thermal emission from the hot atmosphere is strong and molecular absorption features are prominent. Water vapor, H2O, has been definitively detected in HR 8799c's atmosphere. Water produces strong absorption bands in the near-infrared. The spectroscopic signature is clear and unambiguous. At 1000 Kelvin, water exists as vapor, not liquid or ice. The atmosphere contains substantial water vapor, though exact abundances are difficult to measure. Carbon monoxide, CO, is another prominent atmospheric constituent. CO absorption features appear clearly in the spectrum. Carbon monoxide is thermally stable at HR 8799 C's temperature and is expected to be abundant on gas giants. The CO detection confirms the presence of carbon and oxygen in the atmosphere. Methane, CH4, has been searched for but is not definitively detected, or if present, is at very low abundance. This is initially surprising because methane is abundant on Jupiter and Saturn. But at 1000 Kelvin, thermochemical equilibrium favors carbon monoxide over methane. The absence or low abundance of methane tells us the atmosphere is hot and in chemical equilibrium. By measuring the abundances of water, carbon monoxide, and carbon dioxide, astronomers can estimate the atmosphere's carbon-to-oxygen ratio, the relative amounts of carbon and oxygen atoms. For HR 8799c, the Karov ratio appears to be around 0.5 to 0.65, similar to the Sun's ratio of 0.55. This suggests the planet formed from material with solar-like composition. The atmosphere's metallicity, the abundance of elements heavier than helium, appears to be enhanced compared to the star. This is expected. Planets form through accumulation of solid material, rocks, ices, enriching them in heavy elements. Jupiter has 3 to 5 times solar metallicity. HR 8799c appears similar or slightly higher. At 1000 Kelvin, certain materials can condense into clouds. Iron and silicates, compounds of silicon and oxygen, can form solid or liquid droplets. These clouds affect the planet's spectrum, absorbing and scattering light. The presence of clouds makes spectrum interpretation challenging, but also makes the planet more interesting. It has weather. Spectroscopic data can be inverted to estimate the atmosphere's pressure-temperature profile, how temperature changes with altitude. For HR 8799c, temperature likely decreases with altitude in the upper atmosphere, reaching about 1000 to 1100 Kelvin in the photosphere, where thermal emission originates. Deeper in the atmosphere, temperature and pressure increase. HR 8799c's existence raises fundamental questions about planet formation. How does a planet 7 times Jupiter's mass form at 38 Australian dollars? Two main theories compete: core accretion and gravitational instability. Core accretion is the standard model for gas giant formation. It works in stages. First, solid materials, ice and rock, accumulate into a core of perhaps 10 Earth masses. Once the core is massive enough, it gravitationally attracts surrounding gas, building a hydrogen-helium envelope. Jupiter and Saturn are thought to have formed this way. But core accretion faces challenges at 38 Australian dollars. The protoplanetary disk is less dense far from the star, so accumulating a massive core takes longer. And the disk has a limited lifetime, typically a few million years before gas dissipates. Can core accretion build a 7 Jupiter mass planet at 38 Australian dollars in just a few million years? It's questionable. Gravitational instability offers an alternative. If the protoplanetary disk is massive and cool, it can become gravitationally unstable. Dense clumps form and collapse directly into planets without needing a core first. This process is fast, forming planets in thousands of years rather than millions. It works well at large distances where the disk is cool. Several lines of evidence suggest HR 8799c might have formed via gravitational instability. Its large mass and distant orbit fit the profile. The atmosphere's metallicity and Karov ratio are consistent with formation from disk material without extensive solid accretion. And computer simulations show gravitational instability can produce planets at the masses and distances observed. Alternatively, HR 8799c might have formed closer to the star via core accretion, then migrated outward through gravitational interactions with the disk or with other planets. Outward migration is possible, though less common than inward migration. If HR 8799c formed closer in and migrated out, that would resolve the core accretion difficulty at large distances. The existence of 4 massive planets might itself provide clues. Did they all form via the same mechanism? Their spacing suggests resonances, possibly formed through migration. Or perhaps gravitational instability produced multiple planets simultaneously. The system architecture preserves information about formation, if we can decode it. How exactly do astronomers photograph HR 8799c? What technologies make direct imaging possible? Let's explore the sophisticated techniques required. Adaptive optics compensates for atmospheric turbulence, the twinkling of stars caused by air currents. A laser creates an artificial guide star high in the atmosphere. Sensors measure how turbulence distorts the guide star's image hundreds of times per second. Actuators on the telescope mirror deform the mirror to cancel the distortion, sharpening the image dramatically. Coronagraphs block starlight while allowing light from nearby planets to pass. There are several designs. Band-limited coronagraphs use carefully shaped masks to suppress starlight. Vortex coronagraphs use optical vortices, phase shifts that cancel starlight interference style. All aim to create a dark region around the star where planets become visible. Even with adaptive optics and coronagraphs, residual starlight, scattered and diffracted, creates speckles that can mimic planets. Angular differential imaging, ADI, solves this. The telescope tracks the star as Earth rotates, causing the field to rotate. Planets orbit the star and thus rotate with the field. Speckles are instrument artifacts and don't rotate. Subtracting rotated images cancels speckles while preserving planets. Spectral differential imaging, SDI, uses the fact that starlight and planet light have different spectra. By observing simultaneously at multiple wavelengths and comparing images, residual starlight can be identified and subtracted. Planets appear at specific wavelengths, like methane absorption bands, while speckles appear at all wavelengths equally. By imaging HR 8799c over multiple years, astronomers measure its orbital motion. The planet moves slowly. At 38 Australian dollars with a 190-year period, it moves about 2 degrees per year, as seen from Earth. But this motion is detectable, allowing orbit determination and confirming the planets are gravitationally bound to the star, not background objects. Multiple world-class observatories contribute to HR 8799c observations. The Keck Observatory's 10-meter telescopes with adaptive optics and coronagraphs have provided some of the highest resolution images. Gemini's 8-meter telescopes optimize for direct imaging. The VLT's Sphere instrument, designed specifically for planet imaging, delivers exquisite data. Together, they build a comprehensive picture. HR 8799c is one of dozens of directly imaged exoplanets discovered since 2008. How does it compare to its cousins? Beta Pictoris B and C orbit a young A-type star similar to HR 8799. Beta Pic B, at 9 to 13 Jupiter masses orbiting at 9 Australian dollars, is closer to its star than HR 8799c and thus hotter. Beta Pic C, at 8 Jupiter masses orbiting at 2 Australian dollars and 70 cents, is even closer. The Beta Pictoris system is younger, 20 million years, making planets hotter and brighter. 51 Eridani b is a 2 to 3 Jupiter mass planet orbiting at 13 Australian dollars around a young, sun-like star. It's notable for having strong methane absorption, unusual for young, directly imaged planets, which are typically hot enough that methane doesn't form. 51 Eri b is cooler than HR 8799c, about 700 Kelvin versus 1000 Kelvin. PDS 70b and C are remarkable. Planets still embedded in their protoplanetary disk, still forming. They orbit a young T-Tauri star at 20 and 34 Australian dollars. They're actively accreting material from the disk, which produces emission in hydrogen alpha. HR 8799c is older. Formation complete, disk dispersed, but still young on cosmic timescales. AF Leporus b is a 3 Jupiter mass planet orbiting at 8 Australian dollars. It's interesting because its atmosphere shows evidence for disequilibrium chemistry, chemical composition that doesn't match thermochemical equilibrium predictions. This might indicate vertical mixing, bringing deep atmospheric material to observable altitudes. HR 8799c shows some similar features. HR 8799c's uniqueness lies in being part of a 4-planet system, the most planets directly imaged around any single star. It's massive but not the most massive, hot but not the hottest. What makes it special is context. It's one of 4, allowing comparative study. The system is a laboratory for understanding planetary atmospheres, orbits, and interactions. HR 8799c has weather, atmospheric dynamics driven by internal heat, rotation, and possibly residual disk material. What's the climate like on this young giant? Unlike hot Jupiters that receive intense stellar radiation, HR 8799c's heat comes from within, residual formation heat, and ongoing contraction. Stellar heating is negligible at 38 Australian dollars. This internal heating creates a fundamentally different climate than tidally locked planets where dayside and nightside temperatures differ dramatically. We don't know HR 8799c's rotation period, whether it spins in 10 hours like Jupiter or takes days like Venus. Measuring rotation requires detecting periodic variations in brightness or spectral features, which is challenging for such a distant object. But rotation affects atmospheric dynamics. Fast rotation produces banded zonal flows like Jupiter's. Slow rotation might produce different patterns. The atmosphere has vertical structure. Temperature and pressure increase with depth. Near the top, where thermal emission originates, temperature is 1000 Kelvin and pressure is perhaps 0.1 to 1 bar. Deeper down, temperature reaches thousands of Kelvin and pressure reaches hundreds or thousands of bars. Circulation transports heat vertically and horizontally. Different materials condense at different temperatures, creating multiple cloud layers at different altitudes. Iron and silicate clouds might form at 500 to 2000 Kelvin. Below that, magnesium silicates condense. Even deeper, other compounds form clouds. The atmosphere is stratified with distinct cloud decks at different pressures. Horizontal winds redistribute heat across the planet. If rotation is fast, Coriolis forces create zonal jets, east-west bands like Jupiter's Great Red Spot and belts. If rotation is slow, circulation might be more meridional, north-south flow. Without direct observations of cloud patterns, we can't confirm which regime applies. Some observations hint at brightness variations over time, possibly atmospheric variability. Clouds might form and dissipate, storms might appear and fade, or rotational modulation might cause periodic brightness changes. Long-term monitoring is needed to detect and characterize this variability. HR 8799c will remain a prime target for atmospheric studies as new instruments come online. What will future observations reveal? JWST has observed or will observe the HR 8799 system. While JWST isn't optimized for direct imaging at visible wavelengths, its infrared sensitivity and spectroscopic capabilities allow detailed atmospheric characterization. JWST can measure molecular abundances with unprecedented precision, constraining formation models. Ground-based extremely large telescopes, the ELT with its 39-meter mirror, TMT with 30 meters, GMT with 25 meters, will revolutionize direct imaging. Their enormous light-gathering power and angular resolution will image planets fainter and closer to their stars. For HR 8799C specifically, ELTs will obtain ultra-high-resolution spectra revealing detailed atmospheric composition. High-resolution spectroscopy, spectral resolution of 50,000 or more, can detect individual molecular absorption lines and measure Doppler shifts from winds. This technique, successful on hot Jupiters, will be applied to directly image planets. It could measure wind speeds on HR 8799C, detect atmospheric rotation, and map chemistry across the disk. Polarimetry, measuring how light polarization changes upon scattering, can detect cloud particles and characterize their properties. Planets scatter starlight, producing polarization. By measuring this polarization, we infer cloud particle sizes, compositions, and distribution. Future polarimetric observations could map HR 8799C's cloud structure. As decades pass, we'll observe more of HR 8799C's orbit. Full orbital completion requires nearly 200 years, but already we've observed 15+ years, constraining the orbit significantly. Continued monitoring will refine orbital parameters, test for additional planets, and potentially detect orbital perturbations indicating unseen bodies. HR 8799C will increasingly be studied comparatively with its three siblings. Planets B, D, and E orbit at different distances, have different temperatures, and might have different atmospheric compositions. By comparing all four, we map how atmospheric properties vary with orbital distance and temperature in a single system, a powerful test of atmospheric models. What does HR 8799C teach us about planets, formation, and the architecture of planetary systems? First, direct imaging opens new parameter space. Transit and radial velocity methods favor close-orbiting planets. Direct imaging favors distant, massive, young planets. HR 8799C represents a population invisible to other methods, giant planets at tens of AU from their stars. We're discovering the outer solar systems of other stars. Second, young planets like HR 8799C show us atmospheres at formation temperatures. Most exoplanets we study are billions of years old, cooled, evolved. HR 8799C is just 30 million years old, still hot from formation. Its atmosphere preserves information about initial conditions, what the planet was made of when it formed. Third, HR 8799C tests formation theories. Its mass, distance, and atmospheric composition all constrain how it formed. Core accretion versus gravitational instability predict different properties. By measuring HR 8799C's characteristics precisely, we test which formation mechanism operated. Fourth, the four-planet HR 8799 system allows comparative planetology around a single star. Different planets, same star, same formation history, only orbital distance varies. This controlled experiment tests how distance affects mass, temperature, atmosphere, and evolution. Fifth, the system's architecture teaches us about long-term stability. For massive planets orbiting relatively close together should interact gravitationally. Yet the system is stable over billions of years. Understanding this stability informs theories of how planetary systems evolve and whether configurations like ours are common or rare. How does HR 8799c compare to planets in our own solar system? What can it tell us about Jupiter and Saturn's youth? HR 8799c is about 7 times Jupiter's mass, far more massive than any solar system planet. The most massive planet in our system is Jupiter at 318 Earth masses. HR 8799c is roughly 2,100 Earth masses. It's intermediate between planets and brown dwarfs, occupying a regime we don't have locally. But HR 8799c's temperature, 1,000 Kelvin, might resemble young Jupiter. When Jupiter formed 4.5 billion years ago, it too was hot from formation, possibly 1,000 Kelvin or higher. Over billions of years, Jupiter cooled to its current 125 Kelvin. HR 8799c shows us what young Jupiter might have looked like. Both HR 8799c and Jupiter have atmospheres dominated by hydrogen and helium with enriched heavy elements. Both have water vapor, though in different phases. Vapor on hot HR 8799c, ice clouds on cold Jupiter. The basic composition is similar, differing mainly in temperature. HR 8799c orbits at 38 Australian dollars, farther than Neptune at 30 Australian dollars. Jupiter orbits at 5 Australian dollars. If HR 8799c formed in place, it formed in the cold outer disk. If it migrated, it might have originated even farther out. Understanding whether HR 8799c migrated informs whether Jupiter might have migrated in our system's history, a question relevant to the Grand TAC and NICE models. HR 8799c is a window into the past. Not HR 8799's past specifically, but the general past of planetary systems. By studying young systems like HR 8799, we learn what our solar system might have looked like 4.5 billion years ago when the sun was young and planets still glowed with formation heat. 133 light-years away, in the constellation Pegasus, orbits a world we can actually see. HR 8799c, a gas giant 7 times the mass of Jupiter, glowing at 1,000 Kelvin from the heat of its formation, still contracting, still evolving. It appears as a tiny point of light in our most powerful telescopes, separated from its star's glare by adaptive optics that sharpen the atmosphere's blur and coronagraphs that block the star's overwhelming brightness. But it's there, not inferred, not calculated, but seen. A planet around another star photograph. HR 8799c orbits at 38 Australian dollars, roughly Pluto's distance, completing one orbit every 190 years. It shares its system with 3 siblings, planets B, D, and E, forming one of the most remarkable planetary systems known. All four are visible simultaneously in a single image, a family portrait of giant worlds. Its atmosphere tells a story written in spectroscopic signatures. Water vapor absorbing in the infrared, carbon monoxide marking carbon and oxygen, clouds of iron and silicate condensing and evaporating in an alien climate. The atmosphere is hot, 1,000 Kelvin, but cooling, radiating formation energy into the cold of space. At just 30 million years old, HR 8799c is an infant on cosmic timescales. Our solar system is 150 times older. Over hundreds of millions of years to come, HR 8799c will continue cooling and contracting. Its atmosphere will evolve, clouds will form at different altitudes, its spectrum will change. We're seeing it at the beginning of a billion-year journey. HR 8799c represents a turning point in exoplanet science. For the first time, we're not just detecting planets indirectly through their effects on stars. We're seeing them, photographing their light, measuring their spectra, watching them move in their orbits. It's the difference between knowing planets exist and seeing them with our own eyes. The next time you see the constellation Pegasus on an autumn night, the flying horse with its great square marking its body, remember, one of those stars, HR 8799, is surrounded by 4 giant planets. The second planet, HR 8799c, orbits at the distance of Pluto, glowing in infrared from the heat of its birth. We can't see it with our eyes, but our telescopes can. And in seeing it, we glimpse the diversity of worlds the universe creates. The next planet on this list is absolutely fascinating. GJ 1214b, a water world in our cosmic neighborhood. Imagine a world where the oceans don't just cover the surface. They extend hundreds of kilometers deep, enveloping the entire planet in a thick blanket of water and steam. This isn't science fiction. This is GJ 1214b, one of the most intriguing exoplanets ever discovered, a world that has fundamentally challenged our understanding of planetary diversity and what it means for a planet to be habitable. On December 16, 2009, astronomers made an announcement that would captivate the scientific community for years to come. Using the immerse project, a network of small automated telescopes in Arizona specifically designed to monitor nearby red dwarf stars, a team led by David Charbonneau of the Harvard-Smithsonian Center for Astrophysics detected something extraordinary, a super-Earth transiting across the face of its parent star. The discovery wasn't made with billion-dollar space telescopes or massive ground-based observatories. Instead, it came from 8 modest 40-centimeter telescopes, each about the size of a large backyard telescope, proving that sometimes the most profound discoveries come from persistent observation rather than sheer technological might. GJ 1214b orbits the star GJ 1214, a red dwarf located approximately 48 light-years from Earth in the constellation Ophiuchus. In cosmic terms, this is practically our backyard, close enough that future generations might actually send probes to study it directly. The host star, GJ 1214, is what astronomers call an M-dwarf, smaller, cooler, and dimmer than our Sun. With only about 15% of the Sun's mass and 21% of its size, this star represents the most common type of star in our galaxy. It's a faint, reddish ember compared to our brilliant Sun, with a surface temperature of only about 3,000 Kelvin compared to the Sun's 5,800 Kelvin. This proximity to Earth made GJ 1214b one of the first super-Earths available for detailed atmospheric study, positioning it as a crucial benchmark in our understanding of exoplanetary diversity. GJ 1214b is what astronomers call a super-Earth, a planet larger than Earth but smaller than the ice giants Neptune and Uranus. The numbers tell a fascinating story. It's approximately 8.17 times the mass of Earth, about 2.85 times Earth's radius, and roughly 1.87 grams per cubic centimeter. To put this in perspective, Earth has a density of 5.51 g/cm superscript 3, while water has a density of 1 g/cm superscript 3. GJ 1214b's intermediate density immediately told scientists something profound. This world couldn't be made primarily of rock like Earth, nor could it be a gas giant like Neptune. It had to be something different, something we don't have in our own solar system. GJ 1214b hugs its parent star at a distance that would shock anyone familiar with Earth's comfortable orbit. Its orbital distance is only about 0.014 Australian dollars, or about 2.1 million kilometers. For comparison, Mercury, the closest planet to our Sun, orbits at 39 cents and takes 88 days to complete one orbit. GJ-1214b is orbiting more than 25 times closer to its star than Mercury does to the Sun. This proximity has profound consequences. The planet is almost certainly tidally locked, meaning the same hemisphere perpetually faces its star, just as the Moon always shows the same face to Earth. One side experiences eternal day, the other eternal night, with only a twilight ring between them where day and night meet. Despite orbiting so close to its star, GJ-1214b isn't as scorching as you might expect. Because its host star is so cool and dim, the planet receives only about 3.4 times more radiation than Earth received from the Sun. Initial estimates placed its equilibrium temperature at around 393 to 555 Kelvin, 120 to 282 degrees Celsius, or 248 to 540 degrees Fahrenheit, assuming different atmospheric conditions. This is hot, far hotter than Earth's average temperature of 288 Kelvin, but not so extreme that it immediately rules out interesting chemistry or complex atmospheric dynamics. It's comparable to the temperatures inside a hot oven or the surface conditions on Venus. The term super-Earth is somewhat misleading. It doesn't mean a larger version of Earth or even Earth-like. Instead, it's simply a mass classification for planets with masses between Earth's and Neptune's, which is about 17 Earth masses. These worlds can have wildly different compositions, from rocky iron spheres to water worlds to mini-Neptunes shrouded in thick hydrogen atmospheres. GJ-1214b sits right in the middle of this category, representing a type of planet that's apparently common in our galaxy but completely absent from our own solar system. This makes it an invaluable laboratory for understanding planetary formation and evolution. Our solar system has a curious gap. We have the terrestrial planets, Mercury, Venus, Earth, Mars, with masses up to 1 Earth mass, and then we jump straight to the ice giants, Uranus and Neptune, at 14 to 17 Earth masses. There's nothing in between. Yet surveys from NASA's Kepler Space Telescope revealed that super-Earths might be the most common type of planet in the galaxy. This presents a paradox. The most common planetary type in the universe is completely absent from our own solar system. Why? GJ-1214b helps us understand what we're missing. It represents an entirely different class of world. Neither a terrestrial planet nor a gas giant, but something wonderfully strange. From a moment of its discovery, scientists were eager to probe GJ-1214b's atmosphere. The planet's large size relative to its dim star made it ideal for transmission spectroscopy, a technique where astronomers observe starlight filtering through the planet's atmosphere during transits, with different molecules absorbing specific wavelengths of light, leaving telltale fingerprints. Early observations yielded puzzling results. Instead of seeing the expected absorption features from various gases, astronomers found what's called a flat or featureless transmission spectrum. The starlight wasn't being absorbed at specific wavelengths. It was being uniformly diminished across all observed wavelengths. In 2012, observations with the Hubble Space Telescope made headlines. A team led by Zachary Berta-Thompson examined the planet's atmosphere in infrared wavelengths and found no signs of a clear, hydrogen-rich atmosphere. This was revolutionary. There were 3 possible explanations for the flat spectrum. For starters, a steamy atmosphere. The planet could be shrouded in thick water vapor clouds that obscure everything beneath them. Next, a high-altitude haze. Particles suspended high in the atmosphere could be scattering light uniformly, hiding the atmospheric composition. Lastly, a hydrogen-poor atmosphere. The planet might have a heavy atmosphere of molecules like water vapor, nitrogen, or carbon dioxide, rather than the hydrogen expected for a planet of this size. Follow-up studies, particularly those conducted with Hubble between 2012 and 2014, increasingly supported the water world hypothesis. The observation suggested that GJ-1214b likely has an atmosphere dominated by heavier molecules, possibly water vapor, rather than hydrogen. But what does water world really mean? We're not talking about Earth-like oceans under a clear blue sky. Instead, imagine a planet where water in various forms, liquid, vapor, exotic high-pressure ices, makes up a significant fraction of the planet's mass. The atmosphere pressure would be enormous, possibly thousands of times greater than Earth's surface pressure. At such extreme pressures and temperatures, water would exist in phases we never encounter on Earth. Deep within the planet, water might exist as hot ice, crystalline structures that remain solid at temperatures far above water's normal boiling point, held together by immense pressure. When GJ-1214b was discovered, there was initial excitement about its potential habitability. A super-Earth orbiting close to a red dwarf, possibly with water. Could this be a potential abode for life? The answer, unfortunately, is almost certainly no, but the reasons why are scientifically fascinating. GJ-1214b orbits well inside the traditional habitable zone, the region around a star where liquid water could exist on a planet's surface. For the cool red dwarf GJ-1214, the habitable zone lies roughly between 0.035 and 7 cents. GJ-1214b at 0.014 Australian dollars is far too close. With equilibrium temperatures between 120 to 282 degrees Celsius, the planet is far too hot for life as we know it. At these temperatures, water can exist as a liquid at normal pressures, though it might deep underground at high pressures. Most organic molecules would break down. Any atmosphere would be in constant turmoil, with extreme temperature differences between the day and night sides driving violent global weather patterns. Red dwarf stars like GJ-1214 pose additional challenges for habitability. For starters, they're stellar flares. M-dwarfs are prone to violent flares that can blast nearby planets with dangerous radiation. There's also tidal locking to consider. The probable tidally locked state creates extreme temperature gradients. Additionally, high-energy radiation. Even when not flaring, these stars emit significant UV and X-ray radiation during their youth. However, GJ-1214b has prompted scientists to think more broadly about habitability. While the surface is inhospitable, could life exist in different regions? There are a few factors to consider. Firstly, deep ocean layers. If the planet has deep water layers, there might be zones at certain depths where temperature and pressure create stable conditions. Next, the exotic biochemistry. Life based on different chemistry might tolerate conditions we consider extreme. Lastly, the subsurface environments. Protected from surface radiation and temperature extremes, subsurface regions might offer refuges. The broader lesson is that habitability is a spectrum, not a binary classification. GJ-1214b helps us understand the edges of that spectrum. Calculating a planet's composition from millions of kilometers away is one of astronomy's greatest challenges. Scientists use a combination of techniques. By comparing GJ-1214b's mass and radius, scientists can constrain its bulk composition. The planet is too dense to be a pure gas ball, but too light to be purely rocky. Models suggest the planet might consist of an iron silicate core, similar to Earth's core and mantle, making up perhaps 30% of the mass. A massive water layer potentially hundreds of kilometers deep, making up 70% or more of the mass. A thick steam atmosphere extending thousands of kilometers above the surface. There's also the water content debate. Estimates of GJ-1214b's water content vary, depending on the models used. For comparison, Earth's water content is only about 0.05% of its total mass. Even if GJ-1214b is on the low end of estimates, it contains proportionally thousands of times more water than Earth. This leads to implications of deep water. If GJ-1214b truly is a water world with deep oceans, the pressure at depth would be extraordinary, millions of times Earth's surface pressure. Under these conditions, water would transition through multiple exotic ice phases, Ice 7, Ice X, etc. The boundary between ocean and interior might be gradual rather than distinct. There might be no traditional surface as we understand it, just layers of increasingly dense water transitioning from gas to liquid to exotic solid phases. The most recent observations suggest GJ-1214b's atmosphere likely contains chemicals and ratios that are very similar to Earth. The relative absence of hydrogen is itself significant. It suggests that GJ-1214b either formed with little hydrogen to begin with, or that it has lost most of its hydrogen over time through processes like atmospheric escape. The differences are stark. While both planets likely have substantial water, they represent fundamentally different planetary types. Earth is a terrestrial world with a thin water layer on top of a rocky foundation. GJ-1214b might be a rocky core buried under a global water envelope so deep that the pressure at the bottom creates exotic forms of matter. GJ-1214b is sometimes called a Mini-Neptune, and there are interesting parallels. Both Neptune/Uranus and GJ-1214b likely have substantial water/ice layers. All three planets are intermediate between rocky planets and gas giants. All have thick atmospheres. However, the differences are equally important. Neptune and Uranus are much larger. They orbit in cold regions and have frozen water, not liquid or vapor. They have thick hydrogen-helium envelopes above their water layers. They likely have much less water proportionally. GJ-1214b exists in a zoo of super-Earths with diverse properties. 55 Cancri, a rocky super-Earth possibly covered in lava, much hotter than GJ-1214b. Kepler, 22b, another potential water world, but in the habitable zone of Sun-like star. HD9, 7658b, a super-Earth with a thin atmosphere, more like a scaled-up version of Earth. K2-18b, a super-Earth in the habitable zone with water vapor detected in its atmosphere. Each of these worlds tells part of the story of super-Earth diversity. GJ-1214b's particular combination of properties, moderate temperature, likely water-rich composition, nearby location, and observable atmosphere, makes it uniquely valuable for comparative studies. GJ-1214b's existence and properties have forced astronomers to revise planetary formation theories, such as formation location. The planet probably didn't form where it is now. At such a close orbit, the protoplanetary disk would have been too hot for water ice to condense. Instead, GJ-1214b likely formed beyond the snow line, the distance from the star where water can freeze, and then migrated inward over millions of years. Also, water delivery. The planet's high water content suggests it accreted large amounts of icy material during formation. This has implications for understanding how terrestrial planets like Earth get their water. And lastly, atmospheric retention. The fact that GJ-1214b has retained a thick atmosphere despite orbiting so close to its star tells us about atmospheric escape processes and what factors allow planets to keep their atmospheres. Before detailed exoplanet surveys, many scientists expected that planetary systems would be similar to our own, just scaled or modified versions. The discovery of planets like GJ-1214b shattered that assumption. GJ-1214b represents one point in this vast parameter space, helping us map out what types of planets are possible and under what conditions they form. This leads to massive implications for life. While GJ-1214b itself is unlikely to host life, Studying it helps us understand where life might exist elsewhere. This includes things like water availability. If water worlds are common, then water, essential for life as we know it, might be more widespread than we thought. It improves habitable zone refinement. Understanding how planets like GJ 1214b behave helps us better define what habitable really means and where to focus our search for life. And also atmospheric biosignatures. Learning to characterize atmospheres like GJ 1214b's prepares us for eventually detecting biosignatures, chemical signs of life, in the atmospheres of more promising worlds. Kepler mission data suggests that planets like GJ 1214b might be extremely common. Super-Earths orbiting red dwarf stars could number in the billions in our galaxy alone. If many of these are water worlds, it implies water is even more abundant in the universe than we realized. That our solar system might be unusual in lacking this common planet type, and that there are entire classes of planetary environments we've never directly observed. The James Webb Space Telescope, or JWST, launched in December 2021, has revolutionized exoplanet studies. For GJ 1214b specifically, JWST offers. JWST can observe at wavelengths where water vapor, methane, and other molecules have strong signatures, potentially breaking through any hazes or clouds that have obscured previous observations. Meter Mirror, JWST can detect fainter signals than Hubble, allowing more detailed atmospheric characterization. By observing the planet's thermal emission, the heat it radiates, JWST can probe deeper atmospheric layers than transmission spectroscopy alone. Early JWST observations of GJ 1214b and similar planets are expected to finally resolve whether these worlds truly are water worlds or if other compositions could explain their properties. The next generation of ground-based telescopes will also contribute. These include extremely large telescopes, such as the European Extremely Large Telescope, ELT, with its 39-meter mirror, will have the power to conduct detailed atmospheric studies of planets like GJ 1214b, potentially detecting subtle chemical signatures missed by space telescopes. Spectroscopic surveys might also help. Projects like the CARMENES survey continue to discover and characterize planets around red dwarfs, providing a larger sample for comparison with GJ 1214b. While no dedicated mission to GJ 1214b is currently planned, several mission concepts could study it. The Large UV/Optical/IR Surveyor. This proposed NASA flagship mission would have a 15-meter mirror capable of direct imaging and spectroscopy of nearby exoplanets. The Habitable Exoplanet Observatory. Another proposed flagship mission designed to directly image Earth-like planets around nearby stars. The Starshade missions. A starshade, a large external occulter that blocks starlight, could fly in formation with a space telescope, enabling direct observation of planets that are currently too close to their stars to image. On a longer timescale, possibly late 21st or 22nd century, humanity might send interstellar probes to nearby systems. At 48 light-years, GJ 1214 is far beyond current spacecraft capabilities, but proposed concepts like Project Starshot, using laser-push light sails to reach 20% of light speed, could theoretically send miniature probes that would arrive in roughly 240 years. Such future probes could possibly take direct images of the planet, sample its upper atmosphere, measure its magnetic field, detect any moons or ring systems, search for any unexpected phenomena. Any unexpected combinations of chemicals in the atmosphere could indicate active geological processes or, in the most optimistic scenario, biological activity, though this seems very unlikely given the extreme conditions. Long-term monitoring could reveal whether the planet is evolving, losing atmosphere, experiencing climate changes, or showing other temporal variations. GJ-1214b may be a small world orbiting a dim star, but its scientific significance is immense. This planet represents something new, a type of world we've never seen up close, a water world on a scale that doesn't exist in our solar system. It reminds us that the universe is far more creative than we imagined. The neat categories we use to divide planets, terrestrial, gas giant, ice giant, are being supplemented by new categories, water worlds, lava planets, superpuffs, hot Neptunes, and others we haven't discovered yet. For scientists, GJ-1214b is a laboratory. By studying how water behaves under extreme conditions, how atmospheres are structured on super-Earths, and how planets migrate and evolve, we learn fundamental physics and chemistry that applies throughout the universe. For the search for life, GJ-1214b sets boundaries. While this particular world is almost certainly lifeless, understanding it helps us comprehend what separates habitable worlds from uninhabitable ones, and where the boundaries of life's tolerance might lie. And for human imagination, GJ-1214b is an invitation. Just 48 light-years away, close enough that we'll likely have much better data within a few decades, close enough that future generations might see it as the first stop on humanity's journey to the stars, exists a world utterly unlike our own. A world where water rules, where the pressure at depth would instantly crush any visitor from Earth, where the sky glows with endless steam clouds, and where the laws of physics create conditions we can barely imagine. We live in an era where such worlds are transitioning from science fiction to science fact. GJ-1214b is at the forefront of that transition, a real place with real physical properties waiting for us to understand it. In studying this strange water world, we take one more step toward comprehending the magnificent diversity of worlds that populate our galaxy and our place among them. The story of GJ-1214b is still being written. The next chapters, written by JWST, by ground-based telescopes, by future missions, and by generations of scientists yet to come, will reveal whether our current understanding is correct or whether this enigmatic world has even more surprises in store. Whatever we discover, GJ-1214b has already earned its place in the history of planetary science as one of the first worlds to show us that the universe is far stranger and more wonderful than we ever imagined. This next planet is very special. XO-1b Nagoya, one of the first exoplanets to be detected with a transiting method. On a volcanic peak in Hawaii, perched above the clouds at the edge of space, an unusual telescope searches the heavens. It doesn't look like much, just two camera lenses bolted together, resembling a giant pair of binoculars. This is the EXO telescope, built for just $60,000 from commercial equipment. It would make one of the most significant discoveries in the hunt for alien worlds. From September 2003 to September 2005, this telescope monitored tens of thousands of stars, watching for the telltale flicker, a barely perceptible dimming that reveals a planet crossing in front of its star. The team was led by Peter McCullough from the Space Telescope Science Institute, working with both professional and amateur astronomers from across North America and Europe. We wanted to prove that you didn't need millions of dollars to discover planets. The EXO project was about democratizing astronomy, showing that careful work with modest equipment could yield real science. And then they found it. A star in the constellation Corona Borealis, the Northern Crown, 536 light-years from Earth. Every 3.94 days, like clockwork, its light dimmed by 1.7% for about 3 hours. Something was passing in front of it. Something big. But finding a signal was only the beginning. False alarms are common. Eclipsing binary stars, instrumental glitches, or other phenomena can mimic a planet. The discovery had to be confirmed. McCullough's team turned to the powerful telescopes at McDonald Observatory in Texas. Using the radial velocity method, measuring how the star wobbles as the planet's gravity tugs on it, they could determine the planet's mass. If it was massive enough, it had to be a planet, not an imposter. The measurements revealed a world unlike anything in our solar system, nearly as massive as Jupiter, but orbiting incredibly close to its star, closer than Mercury is to our Sun, completing an orbit in less than 4 days. On May 16, 2006, the discovery was announced. The EXO project had found its first planet, EXO 1b. Years later, in 2019, the International Astronomical Union invited countries around the world to name exoplanets. Romania chose EXO 1b, giving it the name Nagoya after the country's second highest mountain peak. Like its namesake mountain rising above the clouds, Nagoya, the planet orbits in the extreme heights of its star, blazing hot under relentless radiation. A world at the edge of survival. Imagine a world where the year lasts less than 4 days, where one side of the planet faces an eternal noon while the other knows only endless night, where temperatures soar to over 900 degrees Celsius, hot enough to melt lead. This is Nagoya, a hot Jupiter. The name seems contradictory, hot Jupiter, but it describes a type of planet that stunned astronomers when they were first discovered in the 1990s. Gas giants like Jupiter, but orbiting terrifyingly close to their stars. Before we discovered hot Jupiters, we thought all planetary systems looked like ours. Rocky planets close in, gas giants far out. Hot Jupiters broke all the rules. They showed us that planets can migrate, that systems can be reshuffled. They fundamentally changed how we think about planet formation. Nagoya orbits its star at just 7.3 million kilometers, about 11 times the star's radius. It's so close that the star's gravity has locked the planet's rotation, forcing one hemisphere to forever face the inferno while the other freezes in eternal darkness. Nagoya is enormous, about 1.3 times the size of Jupiter, but surprisingly light. With a mass just 0.83 times Jupiter's, the planet is less dense than it should be. It's inflated, puffed up like a balloon by the intense heat from its nearby star. Scientists call this the radius anomaly. Many hot Jupiters are larger than they should be, and we're still not entirely sure why. One theory suggests that powerful winds in the upper atmosphere interact with the planet's magnetic field, creating electrical currents that heat the interior. The hotter the planet gets, the more it expands, a feedback loop of heat and inflation. But Nagoya's true revelation lies in its atmosphere. And to read that, scientists would need to split starlight into rainbows. In orbit high above Earth, the Hubble Space Telescope turned its powerful eye toward Nagoya. The mission, to catch the planet during transit, when it passes in front of its star, and analyze the starlight filtering through its atmosphere. Using Hubble's NICMOS instrument, astronomers captured near-infrared light, invisible to human eyes but perfect for detecting molecules. Different molecules absorb different colors of light, leaving a unique fingerprint in the spectrum. What they found was extraordinary. Water vapor, methane, carbon dioxide, and possibly carbon monoxide. Nagoya's atmosphere revealed itself molecule by molecule. The data quality was so high, near the theoretical limits set by photon noise, that scientists could determine the atmospheric composition with unprecedented precision. What was surprising about EXO 1b about Nagoya was the ratio of carbon to oxygen in its atmosphere. It appeared to be carbon-rich, with a C2O ratio near 1, or possibly exceeding it. This is very different from our Sun, which has a C2O ratio of about 0.5. The carbon-to-oxygen ratio is like a cosmic fingerprint. It tells us where a planet might have formed. In a protoplanetary disk, different ices condense at different distances from a star. Water ice forms close in. Carbon monoxide ice forms farther out, where it's colder. If Nagoya formed beyond the water ice line, but inside the carbon monoxide ice line, it would naturally have more carbon than oxygen. This clue suggests the planet didn't form where we find it today. It was born far from its star in the cold outer reaches of the system, and somehow migrated inward to its current hellish orbit. On Nagoya, weather is not measured in days or weeks. It operates on a different scale entirely. The permanent day-night divide creates a temperature difference of 500 degrees or more, driving winds that race around the planet at supersonic speeds. Computer models predict equatorial jet streams moving faster than the planet rotates, a phenomenon called superrotation. These winds approach or exceed the speed of sound, creating shock waves in the atmosphere. Storm systems larger than Earth rage across the face of the planet, mixing hot and cold air in turbulent vortices. But here's what's remarkable. Despite the extreme conditions, Nagoya's atmosphere manages to transport some heat from the blistering day side to the frozen night side. This redistribution of energy affects the planet's thermal structure and determines what we can observe from Earth. Studies of Nagoya's heat emission suggest a relatively efficient heat transport system. Unlike some hot Jupiters that trap heat on their day sides, Nagoya appears to spread it around, though not perfectly. The hottest point on the planet may be offset eastward from the spot directly facing the star, carried there by supersonic winds. For nearly 2 decades, amateur and professional astronomers have kept watch over Nagoya. Every transit is an opportunity, a chance to refine measurements, to search for subtle variations in timing that might reveal hidden companions. Transit timing variations, TTVs, can tell you if there's another planet in the system pulling on the transiting planet. Even from my backyard, I can measure the mid-transit time to within about a minute. When you combine observations from hundreds of amateur astronomers worldwide, you get incredible precision. From 2006 to 2021, observers recorded hundreds of transits. The result? Nagoya's orbit is remarkably stable. Its orbital period, 3.9415049 days, give or take less than a tenth of a second, hasn't varied detectably over 15 years. No timing variations. No hidden planets tugging on Nagoya's orbit. If there are other worlds in the system, they're either very small, very distant, or in orbits that don't interact strongly with a hot Jupiter. Hot Jupiters like Nagoya live on borrowed time. Tidal forces, the same forces that create Earth's ocean tides, constantly pull at both the planet and its star. These forces dissipate energy as heat, and that energy has to come from somewhere. It comes from the orbit itself. Very slowly, Nagoya is spiraling toward its star. We can't detect this orbital decay yet. The change is too small over the 15 years we've been watching. But on timescales of millions or billions of years, the planet's fate is sealed. Eventually, it will fall into its star and be consumed. But that end is far in the future. For now, Nagoya endures, a testament to the strange and violent variety of worlds in our galaxy. Nagoya is not alone. Since the first hot Jupiter was discovered in 1995, astronomers have found hundreds of these extreme worlds. Each one teaches us something new about how planets work. HD 209458b, discovered before Nagoya, shares striking similarities, similar size, similar mass, orbiting a similar star. When scientists compared their atmospheric spectra, they found something remarkable. The two planets' atmospheres look nearly identical in the infrared. This suggests that despite being hundreds of light years apart, they formed and evolved in similar ways. But other hot Jupiters are wildly different. WASP 12b, like Nagoya, appears carbon-rich. Trace 4b is so inflated it's less dense than Cork. Some hot Jupiters have stratospheres with temperature inversions. Others don't. The diversity among hot Jupiters is stunning. We're finding that atmospheric composition, things like the carbon-to-oxygen ratio, can vary dramatically from planet to planet. This diversity is a clue. It tells us about different formation histories, different migration pathways, different amounts of solid material accreted during formation. Theory 1. Disk migration. The planet forms far from its star, beyond the ice line where giant planets are supposed to form. Gravitational interactions with the disk of gas and dust cause it to spiral inward. As the disk dissipates, the planet is left in a close orbit. Theory 2. High eccentricity migration. Gravitational interactions between multiple planets, or, with a distant stellar companion, throw the planet onto a highly elliptical orbit. Over time, tidal forces circularize this orbit, leaving the planet close to its star. How did Nagoya end up where it is? There are three main theories, and each has evidence for and against it. Theory 1. Disk migration. The planet forms far from its star, beyond the ice line where giant planets are supposed to form. Gravitational interactions with the disk of gas and dust cause it to spiral inward. As the disk dissipates, the planet is left in a close orbit. Theory 2. High eccentricity migration. Gravitational interactions between multiple planets, or with a distant stellar companion, throw the planet onto a highly elliptical orbit. Over time, tidal forces circularize this orbit, leaving the planet close to its star. Theory 3. In situ formation. The planet forms right where we find it, close to the star, from material that migrated inward through the disk early in the system's history. For Nagoya, the circular orbit and apparent lack of companion planets point toward either disk migration or in situ formation. But the carbon-rich atmosphere, if confirmed, suggests formation in a colder region of the disk. The puzzle isn't solved yet. The James Webb Space Telescope, the most powerful observatory ever sent into space, is now studying exoplanets like Nagoya with unprecedented precision. Its infrared vision can detect molecules that Hubble couldn't see, measure atmospheric temperatures with exquisite accuracy, and track how heat flows around the planet. JWST could definitively measure Nagoya's carbon-to-oxygen ratio, resolving the question of its formation location. It could detect trace molecules like hydrogen cyanide or ammonia. It could map the planet's thermal structure in 3 dimensions, revealing how winds carry heat around the planet. On the ground, the next generation of extremely large telescopes, with mirrors 30 or 40 meters across, will begin operation in the coming years. These giants will use high-resolution spectroscopy to detect individual molecular species, measure wind speeds through Doppler shifts, and potentially even detect magnetic fields. For Nagoya, this means answers to questions we've been asking for nearly 2 decades. What is the true composition of its atmosphere? How efficient is its heat redistribution? Does it have clouds of exotic minerals raining through its atmosphere? Are there photochemical processes creating molecules that shouldn't exist in equilibrium? We now know of over 5,000 planets beyond our solar system. Hot Jupiters like Nagoya make up just a small fraction of this diversity. Perhaps 1% of all Sun-like stars host a hot Jupiter. But these extreme worlds punch above their weight in scientific importance. They're laboratories for extreme physics, places where we can study atmospheric chemistry at temperatures impossible to recreate on Earth, where we can watch tidal forces reshape entire worlds, where we can test our theories of planet formation in conditions far removed from our own solar system. Every exoplanet we study teaches us something about the possibilities. Hot Jupiters showed us that planets can migrate. Super-Earths showed us that planets can exist in sizes we don't have in our solar system. Mini-Neptunes, lava worlds, planets orbiting binary stars. Each discovery expands our understanding of what's possible. And perhaps most importantly, studying planets like Nagoya, worlds so different from our own, gives us context for understanding Earth. We are one planet among many. Our conditions, our history, our atmosphere and oceans, these are not universal truths, but specific outcomes of our particular formation and evolution. On a mountaintop in Hawaii, the EXO telescope still watches the skies. It discovered 6 planets during its operational lifetime, 5 hot Jupiters and 1 possible brown dwarf. But its first discovery, EXO 1b, remains its most extensively studied. Today, amateur astronomers around the world continue to observe Nagoya's transits, contributing to a global effort to understand this distant world. Their observations join data from the world's most powerful telescopes, Hubble, JWST, and others yet to come. Nagoya, 536 light-years from home. A world of extremes, scorching heat and supersonic winds, carbon clouds, and eternal storms. A planet that shouldn't exist by the rules we thought we knew, orbiting in defiance of our expectations. But there it is, revealed transit by transit, spectrum by spectrum. A testament to the power of careful observation, collaborative science, and human curiosity about the cosmos. Every 3.94 days, like clockwork, Nagoya passes in front of its star. And from Earth we watch, we measure, we learn. One world among trillions. One story among countless others waiting to be told. For our next planet on the list, it's time to take a journey to a planet of glass and storms. HD 189733b. The Blue World. For decades, we've called Earth the Blue Marble. The only blue world we knew, oceans, clouds, life. But 64 light-years away, in a constellation called Vulpecula, the little fox, there's another blue planet. HD 189733b. From a distance, it looks almost friendly. But don't be deceived. This is a planet where the rain is made of glass, where winds scream at 7 times the speed of sound, where the air itself smells like rotten eggs. This is a world that should never have existed, and studying it has changed everything we thought we knew about planets. October 5, 2005, a team of French astronomers detected something extraordinary. A star in Vulpecula was dimming, right on schedule, every 2.2 days. The cause? A planet the size of Jupiter, passing in front of its star. The planet was designated HD 189733b after its host star. At just 64.5 light-years from Earth, it became the closest transiting hot Jupiter ever discovered, and the brightest. That combination would make it the most intensively studied exoplanet in history. The transit was deep, blocking 3% of the star's light, one of the largest transit signals ever measured. This made HD 189733b the perfect laboratory for a new science, characterizing the atmospheres of alien worlds. HD 189733 is not a single star, but a binary system. The primary star, HD 189733a, is an orange dwarf, AK 1.5, type star slightly smaller and cooler than our Sun. It has 81% of the Sun's mass and shines with just a third of its brightness. Far from the primary, over 200 astronomical units away, more than 5 times Neptune's distance from our Sun, orbits a faint red dwarf companion. HD 189733b is a dim M-type star, gravitationally bound to the system but too distant to affect the planet. It takes roughly 3,200 years to complete one orbit. But it's the planet that defies imagination. HD 189733b orbits at just 0.03 astronomical units from its star, 13 times closer to its Sun than Mercury is to ours. At this distance, the planet completes an entire orbit in 53 hours. 2 days, 5 hours. That's a year on HD 189733b. Moving through space at 152 kilometers per second, 340,000 miles per hour, the planet is locked in a death grip with its star. Tidal forces have frozen its rotation. One side faces eternal noon, the other perpetual night. In 2007, the Spitzer Space Telescope turned its infrared eye toward HD 189733b. For 33 consecutive hours, Spitzer watched the planet orbit its star, measuring how its brightness changed as different portions of the planet rotated into view. What we did was revolutionary at the time. We couldn't resolve the planet into a disk. It's just a point of light. But by measuring how that point got brighter and dimmer as the planet rotated, we could map its temperature. We created the first weather map of an alien world. The map revealed a world of extremes. The night side temperature, 973 Kelvin, 700 degrees Celsius, hot enough to melt aluminum. The day side, 1,212 Kelvin, 940 degrees Celsius, approaching the melting point of silver. But something was strange. The hottest spot on the planet wasn't directly facing the star. It was offset, shifted eastward by about 30 degrees. Something was carrying heat around the planet. Winds. In 2012, astronomers at the University of Warwick made a chilling discovery. Using high-resolution spectroscopy, they measured the wind speeds on HD 189733b. The result, 8,700 kilometers per hour, 5,400 miles per hour, 7 times the speed of sound. To put that in perspective, the fastest winds ever recorded on Earth, during Tropical Cyclone Olivia in 1996, reached 253 miles per hour. The most powerful hurricane winds top out around 200 miles per hour. On HD 189733b, the wind blows more than 20 times faster. These supersonic winds are driven by the temperature difference between day and night. Even though the difference is only 240 degrees Celsius, relatively small for a hot Jupiter, the pressure gradient is enormous. The atmosphere races from the scorching day side toward the night side in a desperate attempt to reach equilibrium. But the winds carry more than heat. They carry death. In the upper atmosphere, where temperatures are cooler, silicate compounds condense out of the vapor. On Earth, these would be minerals, solid rock. But on HD 189733b, they form as tiny droplets of molten glass. Magnesium silicate, primarily. Particles between 1/100th and 1/10th of a micrometer across. Imagine standing on this planet. If you could somehow survive, you'd see blue haze above you, thick with these glassy particles. And then the wind would hit. These microscopic shards wouldn't fall like rain on Earth. They'd come at you sideways, horizontally, at thousands of miles per hour. It would be like standing in a sandblaster, except instead of sand, it's glass, and it's moving at supersonic speeds. On Earth, rain falls vertically because gravity is the dominant force. On HD 189733b, the winds are so powerful that they overwhelm gravity. The glass rain doesn't fall, it flies. In 2013, astronomers used the Hubble Space Telescope to do something unprecedented. They measured the actual visible color of HD 189733b. Not an artist's impression, not a simulation. The real color, determined from reflected starlight. The result stunned the world. Deep cobalt blue, more intensely blue than Earth has ever been. It looked like paradise. But the reason for the color revealed just how alien this world truly is. On Earth, the sky is blue because of Rayleigh scattering. Air molecules scatter blue light more than red. The oceans reflect that blue light back to space, creating our planet's characteristic hue. HD 189733b has no ocean. Its blue color comes from the very particles that make its weather so deadly. The silicate glass droplets in the high atmosphere scatter blue light preferentially, just like air molecules do on Earth. But instead of creating a serene sky, they create a haze of death. NASA called it one of the most terrifying destinations in the galaxy. A beautiful blue world that rains glass, sideways, in 5,000 mile per hour winds. In 2024, the James Webb Space Telescope, the most powerful observatory ever built, turned its gaze toward HD 189733b. What it found added a new dimension to our understanding of this alien world. Literally, we detected hydrogen sulfide, H2S. It's the first time we've found this molecule outside our solar system. And if you could somehow smell the atmosphere of HD 189733b, it would reek of rotten eggs. Hydrogen sulfide, the compound that gives rotten eggs their distinctive stench. On Earth, it's produced by decaying organic matter and volcanic activity. On HD 189733b, it forms through high-temperature chemistry in the planet's atmosphere. But the discovery is about more than smell. Sulfur is a crucial element in planet formation. Measuring sulfur abundance helps astronomers understand where and how giant planets form. In 2007, HD 189733b made history. Using the Spitzer Space Telescope, astronomers detected the unmistakable signature of water vapor in its atmosphere. It was only the second exoplanet where water had been conclusively found. The following year, Hubble confirmed the detection and found something else, methane. It was the first time an organic molecule had been detected on a planet orbiting another star. Finding water and methane on HD 189733b was a watershed moment. It proved that we could characterize the chemical composition of alien atmospheres. These are the same techniques we'll use to search for signs of life on Earth-like planets. HD 189733b was our training ground. Over the years, more molecules have been detected. Carbon dioxide in 2008, carbon monoxide, sodium, and lithium in 2024. Each discovery adds another piece to the puzzle of this planet's composition and chemistry. But at 1,000 degrees Celsius, the water exists only as vapor. It will never condense into clouds. It will never rain. The atmosphere is far too hot. Yet the discovery revolutionized exoplanet science. In 2014, NASA made a puzzling announcement. HD 189733b, along with two other hot Jupiters, appeared to have surprisingly dry atmospheres. Despite the water detection, the abundance was lower than expected. This finding challenged our understanding of how these planets form. Jupiter is rich in water ice. It formed beyond the snow line where water could freeze. We expected hot Jupiters to have similar compositions. But HD 189733b seemed depleted. The mystery deepened in 2024 when Webb observations ruled out the previously suspected abundance of methane. The planet's chemistry was proving more complex than anyone anticipated. HD 189733b has been a planet of firsts. The first exoplanet to have a thermal map constructed. The first to have its overall color determined. The first transiting planet caught in X-rays. The first with confirmed carbon dioxide in its atmosphere. In 2010, observations with the Hubble Space Telescope detected something extraordinary. The planet is evaporating. Atomic hydrogen streaming away from the planet at rates between 1 and 100 gigagrams per second. The intense radiation from its nearby star is slowly stripping away its atmosphere. The planet won't survive forever. On timescales of billions of years, HD 189733b is doomed. HD 189733b is a hot Jupiter, a gas giant orbiting frighteningly close to its star. Before the mid-1990s, we didn't know such planets existed. Our solar system taught us that rocky planets orbit close in, gas giants orbit far out. Hot Jupiters broke all the rules. Hot Jupiters shouldn't exist, according to planet formation theory. Giant planets form beyond the ice line where there's enough solid material to build a core. At the distances where we find hot Jupiters, temperatures are too high. So either these planets formed far out and migrated inward, or our theories were completely wrong. HD 189733b is massive, 1.13 times Jupiter's mass, but slightly larger, with a radius 1.14 times Jupiter's. Like many hot Jupiters, it's inflated. The intense stellar radiation heats the planet, causing its atmosphere to expand. At just 0.03 astronomical units from its star, 13 times closer than Mercury to the Sun, HD 189733b is tidally locked. Its rotation period equals its orbital period, 2.2 days. One hemisphere permanently faces the star. The other faces away into eternal darkness. One of the most important discoveries about HD 189733b came from that first thermal map. The night side is only about 240 degrees cooler than the day side. That may sound like a lot, but for a tidally locked planet, it's remarkably efficient heat redistribution. Some hot Jupiters trap heat on their day sides, creating temperature differences of 1,000 degrees or more. HD 18973-3b's atmosphere does a much better job of transporting energy from day to night. That's what those supersonic winds are doing, frantically trying to equalize temperatures. The hotspot shifted 30 degrees east of the substellar point tells us about the balance between wind speed and radiation. Heat is being carried eastward faster than it can be radiated away. This offset is predicted by atmospheric circulation models and confirmed by observations. HD 189733b has become what scientists call a benchmark planet, a standard against which all other hot Jupiters are compared. It's close enough to study in detail, bright enough to get high-quality data, and it transits so we can probe its atmosphere. Compared to HD 209458b, HD 189733b is hotter, windier, and bluer. Compared to WASP 12b, it's cooler and less inflated. Each hot Jupiter is unique, shaped by its formation history, migration pathway, and current stellar environment. HD 189733b is a giant in the field of exoplanets. It's one of the anchor points for our understanding. Every new detection technique, every new instrument, HD 189733b is often the first planet we point at. It's our Rosetta Stone for hot Jupiters. The diversity among hot Jupiters tells us that planetary formation and evolution are more complex than we imagined. Some hot Jupiters have temperature inversions in their atmospheres, hot stratospheres. HD 189733b doesn't. Some have clouds of titanium oxide. HD 189733b has clouds of glass. Remember that distant companion star? HD 189733b. The red dwarf orbiting 216 astronomical units away? It posed a puzzle. The primary star, HD 189733a, spins once every 12 days. Its rotation rate and X-ray emissions suggest an age of only 600 to 700 million years, a relatively young star. But the companion's low activity indicates it's much older, 6 to 9 billion years. How can two stars in the same system have such different ages? The answer may lie with the planet. Tidal interactions between HD 189733b and its host star are transferring angular momentum from the planet to the star, spinning the star up. This makes the star appear younger than it really is. The planet is literally keeping its star young. For nearly 2 decades, astronomers have monitored HD 189733b, hundreds of transits observed, thousands of spectra collected, and in 2021, something unexpected appeared: transit timing variations. The planet's transits weren't happening exactly when predicted. The variations were small, minutes at most, but they suggest the presence of other bodies in the system. Perhaps another planet, tugging gravitationally on HD 189733b, or perhaps something else we haven't yet identified. Earlier claims that the planet's orbit causes stellar flaring have been debunked, but the timing variations are real. The HD 189733 system may be more complex than we thought. HD 189733b taught us that we could map the weather on alien worlds. That seemed impossible before 2007. It showed us we could detect molecules, water, methane, carbon dioxide, in exoplanet atmospheres. It proved the techniques that we now use routinely. And with Webb detecting hydrogen sulfide, we're learning about sulfur chemistry on other worlds. It's expanding our understanding of planet formation. Most importantly, HD 189733b showed us the incredible diversity of planets in our galaxy. We're not just finding other Earths or other Jupiters. We're finding entire new categories of worlds. HD 189733b has taught us about atmospheric dynamics in extreme environments. about heat transport on tidally locked worlds, about the chemistry possible at temperatures exceeding 1,000 degrees, about how planets can alter their host stars. It's shown us that planets can have radically different compositions than we expected, that weather patterns can operate at speeds that dwarf anything in our solar system, that beauty and lethality can coexist. The James Webb Space Telescope has only begun its study of HD 189733b. Future observations will map the planet's three-dimensional thermal structure, detect additional molecules, measure wind speeds at different altitudes, perhaps even image the planet directly. Ground-based, extremely large telescopes, with mirrors 30 or 40 meters across, will use high-resolution spectroscopy to study the planet in unprecedented detail. They'll measure day-to-night temperature differences at specific wavelengths, track individual storm systems, detect magnetic fields. Future missions like Ariel will place HD 189733b in context by surveying thousands of exoplanet atmospheres. We'll learn how common or rare its characteristics are, whether glass rain is a common weather phenomenon on hot Jupiters or something unique to this world. 64 light-years from Earth, a planet the color of a tropical ocean but with the climate of hell, where glass rains sideways at supersonic speeds, where the air smells of rotten eggs and the wind would tear you apart in seconds. HD 189733b will never harbor life. No liquid water, no solid surface, temperatures that would vaporize almost any molecule we know. But in studying this hostile world, we've learned how to characterize alien atmospheres, how to detect molecules across light years of space, how to map weather on distant worlds. The techniques pioneered on HD 189733b are now being applied to smaller, cooler, more Earth-like worlds. Planets where liquid water might flow, where temperatures are moderate, where perhaps life might exist. When we finally detect biosignatures on another world, oxygen, methane, perhaps something we haven't even imagined, we'll have HD 189733b to thank. This deadly blue world was our training ground, our benchmark, our teacher. Every 2.2 days, HD 189733b crosses the face of its star. And from Earth, 64 light-years away, we watch. We measure. We learn. One blue world among countless others. One story in an infinite galaxy. But what a story it is. Next, let's take a look at the Inferno world KLT 9b, the hottest planet ever discovered. Out there, in the vast cathedral of space, 670 light-years from Earth, orbits a world that defies imagination. A planet so extreme, so impossibly hostile, that it shouldn't exist at all. This is KLT 9b, a world where iron rains from the sky, where molecules are torn apart by sheer heat, and where the very atmosphere is being stripped away into the void. This is the story of humanity's encounter with hell incarnate. The year was 2014. While most of the world slept, a small robotic telescope in Arizona was watching the heavens. Not one of the giant observatories that Grace magazine covers, but something humbler, part of the Kilo-degree Extremely Little Telescope Project, or KLT. 2 telescopes, one in each hemisphere, scanning hundreds of thousands of stars each night, looking for something extraordinary in the ordinary. The telltale dimming of starlight that signals a planet passing between us and its sun. We're looking for shadows, essentially, when a planet transits its star, passes directly in front of it from our perspective. The starlight dims ever so slightly. It's like trying to spot a firefly crossing in front of a lighthouse beam from hundreds of miles away. On the night of March 12, 2014, KLT detected something in the constellation Cygnus. Star HD 195689, a massive blue-white star nearly twice the size of our Sun and burning 3 times as hot, had dimmed by just over 1%. Something enormous was orbiting that star. Something that would take 3 years of follow-up observations, data analysis, and peer review before the team was ready to announce what they'd found. In June 2017, the discovery was made public, and the exoplanet community was stunned. Imagine Jupiter, already a giant nearly 11 times wider than Earth, massive enough to swallow over 1,300 Earths inside it. Now imagine a planet nearly 3 times Jupiter's mass, but puffed up by unimaginable heat to almost twice Jupiter's size. That's KLT-9b. But size tells only part of the story. The real terror of KLT-9b lies in its proximity to its parent star. The planet orbits at just 4.5 million kilometers from its stellar furnace, less than 1/20th the distance between Mercury and our Sun. To put that in perspective, if you could stand on KLT-9b, which you couldn't because you'd be instantly vaporized, the star would loom 40 times larger in the sky than the Sun appears from Earth. It would fill roughly a quarter of the entire sky. One orbit takes just 36 hours. A year and a half here on Earth is 365 days. On KLT-9b, that same time period contains nearly 250 years. But it's not the orbital mechanics that make KLT-9b truly extraordinary. It's the temperature. On the day side of this tidally locked world, the side that perpetually faces its star, temperatures soar to 4,600 Kelvin. That's roughly 7,800 degrees Fahrenheit. 4,300 degrees Celsius. That's hotter than the surface of some stars. Let's ground this in something tangible. The hottest temperature ever recorded on Earth's surface was 56.7 degrees Celsius, 134 degrees Fahrenheit, in Death Valley, California. That's hot enough to kill unprotected humans in hours. The melting point of aluminum is 660 degrees Celsius. Molten lava erupting from a volcano reaches about 1,200 degrees. The flame of an oxyacetylene welding torch, one of the hottest things we routinely create on Earth, burns at 3,500 degrees Celsius. KLT-9b's day side is nearly 1,000 degrees hotter than that welding torch. At these temperatures, not even molecules can survive. On Earth, water exists as a stable molecule, 2 hydrogen atoms bonded to 1 oxygen. In KLT-9b's atmosphere, such stability is impossible. At 4,600 Kelvin, molecules are being ripped apart. Water can't exist as H2O. It's torn into individual hydrogen and oxygen atoms. Even molecular hydrogen, H2, one of the most stable bonds in nature, gets dissociated. Metals that we think of as solid, iron, magnesium, sodium, they're not just molten, they're vaporized and floating in the atmosphere. The atmosphere of KLT-9b is unlike anything else we've found. Spectroscopic observations from the Hubble Space Telescope and ground-based instruments have detected gaseous iron and titanium. Imagine clouds not of water vapor, but of vaporized metals, swirling through the planet's upper atmosphere. But perhaps the most dramatic feature of KLT-9b is what's happening to the planet itself. It's dying. The intense radiation from the parent star isn't just heating KLT-9b, it's tearing it apart. Every second, the planet loses an estimated 10 to 100 million kilograms of atmosphere to space. That might sound like a lot, and it is, but KLT-9b is so massive that even at this rate, it would take trillions of years to completely evaporate. The planet is essentially boiling off into space. The day side is so hot that atmospheric particles reach escape velocity. We're watching a planet slowly self-destruct on cosmic timescales. This atmospheric escape creates a comet-like tail of material trailing behind KLT-9b as it hurtles around its star, a visible testament to the violence happening on this world. Weather on Earth is driven by temperature differences between day and night, between equator and poles, between land and sea. These differences create winds, storms, the cycles of rain and drought that shape our world. Now, imagine weather driven by temperature differences not of tens of degrees, but of thousands. KLT 9b is tidally locked, meaning one side perpetually faces its star while the other side faces eternal darkness. The day side bakes at 4,600 Kelvin. The night side, shielded from the star's direct radiation, cools to a comparatively frigid 2,200 Kelvin, still hot enough to vaporize lead, but less than half the temperature of the day side. This temperature difference drives winds of unimaginable ferocity. We're talking about supersonic winds, potentially reaching thousands of kilometers per hour, as the superheated atmosphere on the day side rushes toward the night side in a futile attempt to achieve equilibrium. Computer models suggest these winds could reach speeds of 5,000 to 10,000 kilometers per hour. For comparison, Earth's fastest recorded wind speed during Tropical Cyclone Olivia in 1996 was 408 kilometers per hour. But the most exotic weather phenomenon on KLT 9b might be something straight out of science fiction: iron rain. As the metallic vapors from the day side are swept by those tremendous winds to the night side, they begin to cool. Not enough to solidify. Even the night side is too hot for that, but enough for iron and other metals to potentially condense into liquid droplets. Iron rain, falling through an atmosphere hot enough to melt steel. Studying KLT 9b presents enormous challenges. At 670 light-years away, the planet itself is far too small and dim to image directly. Everything we know comes from indirect observations: the dimming of starlight during transits, the spectrum of light filtered through the planet's atmosphere, the subtle gravitational tugs on the parent star. We're essentially doing astronomy at the limits of what's possible. When KLT 9b passes in front of its star, a tiny fraction of the starlight passes through the planet's atmosphere. That light carries a fingerprint, absorption lines that tell us what elements are present. But the signal is incredibly weak. It's like trying to analyze a whisper in a hurricane. Each observation requires careful coordination. The James Webb Space Telescope, humanity's most powerful space observatory, has been used to study KLT 9b's atmosphere in unprecedented detail. Multiple observations during planetary transits and eclipses build up a picture, piece by piece. One of the most significant challenges is understanding the chemistry. At such extreme temperatures, familiar rules don't apply. We're having to rewrite our chemistry textbooks for these conditions. Chemical reactions that would never happen at earthly temperatures become possible. Molecules that would be stable in cooler environments are destroyed. It's forced us to develop entirely new models of atmospheric chemistry. But perhaps the greatest puzzle is simply, why does KLT 9b exist at all? According to our best theories of planetary formation, planets like KLT 9b, massive gas giant worlds, should form in the cold outer reaches of their solar systems, far from their parent stars, where there's enough material and cold enough temperatures for gas to condense. Jupiter, in our own solar system, formed beyond the asteroid belt. So how did KLT 9b end up in an orbit closer to its star than Mercury is to the Sun? The answer is migration. We think KLT 9b formed much farther out, perhaps billions of kilometers from its star, in a region where gas giant formation is favored. Then, through complex gravitational interactions, maybe with other planets, maybe with the protoplanetary disk itself, it spiraled inward over millions of years. This process, called planetary migration, has revolutionized our understanding of how solar systems evolve. Planets aren't fixed in their orbits. They can move, sometimes dramatically, especially in young solar systems where there's still gas and dust around. But here's the disturbing question. How much longer does KLT 9b have? Is KLT 9b still migrating inward? Will it eventually spiral into its star, consumed in a final cataclysmic collision? Or has it reached a stable orbit, where it will remain for billions of years, slowly bleeding its atmosphere into space? The truth is, we don't know. The timescales of planetary migration are difficult to predict precisely. But one thing is certain, KLT 9b star is massive and hot, and stars like that burn through their fuel quickly. In a few 100 million years, maybe 1 billion at most, that star will swell into a red giant. When it does, KLT 9b will be engulfed. The planet's fate is sealed, one way or another. KLT 9b isn't just a cosmic curiosity, it's a laboratory. A place where nature conducts experiments under conditions we could never recreate on Earth. Since the first hot Jupiter, 51 Pegasi b, was discovered in 1995, we've found thousands of exoplanets. Each one teaches us something new about the incredible diversity of worlds that exist beyond our solar system. But KLT 9b occupies an extreme end of this spectrum. By studying it, we're learning about the physics of extreme heat and how matter behaves at the edge of stellar temperatures, the dynamics of atmospheric escape, and how planets lose their envelopes, the chemistry of exotic atmospheres where familiar molecules can't exist, the evolution of planetary systems, and the dramatic migrations that shape them. Every extreme world we find expands our understanding of what's possible. KLT 9b shows us that planets can exist in environments we thought were too hostile. It challenges our models, forces us to think harder, calculate more carefully. That's what makes this work exciting. We're constantly being surprised. The discovery of worlds like KLT 9b has also reshaped our search for life. For decades, we focused on planets like Earth, rocky worlds at comfortable temperatures. But now we know that planets exist in staggering variety. Some might harbor life in forms we haven't imagined. KLT 9b itself is almost certainly lifeless. No known form of life could survive its inferno. But by understanding the full range of planetary environments, from frozen ice worlds to hellish hot Jupiters, we better understand where the boundaries of habitability truly lie. The study of KLT 9b is far from over. The next generation of telescopes, ground-based giants with mirrors 30 meters across, and new space observatories with capabilities beyond even James Webb, will observe this world with unprecedented detail. We want to map KLT 9b's atmosphere. Not just know what chemicals are there, but where they are, how the composition changes from the day side to the night side, from the upper atmosphere to deeper layers. We want to watch the weather in real time, track those supersonic winds, maybe even see the iron clouds form. Future missions might even be able to detect the planet's magnetic field, if it has one, or measure the precise rate of atmospheric loss, helping us understand not just KLT 9b's fate, but the evolution of hot Jupiters throughout the galaxy. And KLT 9b may not remain the record holder forever. The universe is vast, and we've barely begun our census of its worlds. Somewhere out there might be planets even more extreme, worlds closer to their stars, hotter still, perhaps even disrupting at the Roche limit where tidal forces tear them apart. Every time we think we've found the limit, nature surprises us. KLT 9b hangs in space, a world of extremes, a testament to the creativity of cosmic forces. While we sleep under familiar stars, this inferno world completes dozens of orbits, its atmosphere screaming with winds that would tear continents apart, its skies glowing with vaporized metals, its very substance slowly bleeding into the void. On Earth, astronomers continue their patient work, gathering photons that began their journey when the pharaohs were building pyramids, light that has traveled for 670 years to tell us stories of a world we may never visit. KLT 9b reminds us that the universe is stranger and more wondrous than we imagined. That planets come in infinite varieties. That nature experiments on scales we're only beginning to comprehend. Out there, in the darkness between stars, thousands of worlds await discovery. Some may be havens for life. Others, like KLT 9b, may be hells beyond imagination. But each one, each distant world circling an alien sun, expands our perspective, challenges our understanding, and invites us to keep looking upward, to keep wondering. Because in the end, the quest to understand these distant worlds is really a quest to understand our own place in the cosmos. And that journey has only just begun. This has been the Inferno World, KLT 9b. To learn more about exoplanet research and the ongoing search for worlds beyond our solar system, visit NASA's Exoplanet Exploration Program and follow the latest discoveries from missions like TESS, James Webb, and the next generation of planet hunters. The universe is vast. The search continues. If you think one sun is enough, you might not be ready for this next planet. The remarkable world of PH1, the planet with 4 suns. For billions of years, humans gazed at the night sky and saw only points of light, distant, mysterious, untouchable. We wondered, are there other worlds out there? And if so, what strange and wondrous forms might they take? Today, we know the answer. There are worlds beyond counting. Worlds of fire and ice. Worlds larger than Jupiter, smaller than Mercury. But among all the exoplanets we've discovered, more than 5,000 at last count, one stands apart for its sheer audacity. October 2012. While most of the world slept, a volunteer named Kian Jek sat at his computer in California doing something extraordinary. He was hunting planets. Jek was part of Planet Hunters, a citizen science project where ordinary people help astronomers analyze data from NASA's Kepler Space Telescope. For hours, he'd been examining light curves, measurements of how bright distant stars appear over time. And he learned to look for something specific, a tiny, periodic dip in starlight. When a planet passes in front of its star, an event called a transit, it blocks a small portion of the star's light. For an Earth-sized world, the dip is less than 1%. Blink, and you'd miss it. What Kian found wasn't a typical signal. The light curve showed dips from not one star, but 2 stars orbiting each other, and something was passing in front of both of them. Robert Gagliano, another volunteer in Hawaii, independently noticed the same anomaly. Within hours, professional astronomers were alerted. What these 2 citizen scientists had found would rewrite the textbooks on planetary formation. The confirmation process began immediately. Astronomers at Yale, led by Dr. Meg Schwam, initiated follow-up observations using ground-based telescopes. They needed to rule out false positives, background eclipsing binaries, stellar pulsations, any phenomenon that could mimic a planet's transit. We used radial velocity measurements, analyzing how the stars wobble due to gravitational pull. We examined the depth and shape of the transits. Every test pointed to the same conclusion. This was real. This was a planet. On October 15, 2012, the discovery was announced. The world met PH1, Planet Hunters 1, the first exoplanet discovered by citizen scientists, and one of the most peculiar worlds ever found. Imagine standing on a world where, when you look up, you see not one sun, not 2, but 4 stars illuminating your sky. PH1 orbits in a quadrupole star system, 5,000 light-years from Earth in the constellation Cygnus, the Swan. 2 stars, Kepler, 64a and b, dance around each other in a tight embrace, separated by just 20 million kilometers, closer than Mercury orbits our Sun. Every 20 days, this stellar pair completes one orbit. And around both of them, like a moon circling a planet, travels PH1, a Neptune-sized world 6 times wider than Earth, completing its orbital journey every 138 days. But the system doesn't end there. 1,000 astronomical units away, 1,000 times the distance from Earth to our Sun, 2 more stars orbit this entire cosmic arrangement. A binary orbiting a binary. A planetary system within a stellar system within yet another stellar system. When we first modeled this system, we thought this shouldn't be stable. The gravitational interactions should be chaotic. But PH1 found a way. It occupies what we call a circumbinary habitable zone. Not habitable for life, but habitable for planetary orbits. To understand why PH1 is so remarkable, we need to journey back 4.5 billion years to when this system was born. Planets form from disks of gas and dust surrounding young stars. In a single star system like our own, this process is relatively straightforward. But in a binary system, the gravitational tug-of-war between 2 stars creates gaps and resonances in the disk. Material gets cleared out. The environment becomes turbulent, hostile to planetary formation. When Kepler first started finding circumbinary planets, we were shocked. The conventional wisdom was that planets couldn't form this close to binary stars. PH1 took that surprise and amplified it. Not just 2 stars, but 4. It's planetary formation on hard mode. Computer simulations suggest that for every successful planet like PH1, dozens or hundreds of planetary embryos must have been ejected or destroyed. PH1 is a survivor, a world that beat tremendous odds simply to exist. So what is PH1 like? With a radius 6 times that of Earth and a mass estimated at 169 Earth masses, it's a gas giant in the Neptune class. No solid surface exists beneath those cloud tops, just layers of hydrogen and helium, growing denser and hotter as you descend, until eventually the gas becomes so compressed it transitions into something between liquid and gas, a supercritical fluid. The temperature at its cloud tops likely hovers around minus 200 degrees Celsius. Winds rage at hundreds of kilometers per hour, driven by the complex heating from 2 nearby suns. In the upper atmosphere, methane ice crystals might form delicate, high-altitude clouds. Deeper down, ammonia compounds create bands and zones of color, perhaps pale blues, greens, and whites. Can a world like PH1 harbor life? Not the planet itself. Life as we know it requires solid surfaces or at least stable liquid water. But consider this. In our own solar system, Jupiter and Saturn host dozens of moons. Some, like Europa and Enceladus, hide vast liquid water oceans beneath their icy shells. If PH1 has large moons, and there's no reason to think it doesn't, those moons could be heated by tidal forces. The planet's gravity would need these moons, generating internal heat. Combined with radiation from 4 suns, you could have liquid water. You could have chemistry. You could have life. Imagine an exomoon orbiting PH1. On its surface, you'd see 2 bright suns dominating the sky, casting double shadows on icy plains. PH1 itself would loom huge overhead, perhaps 20 times larger than our moon appears from Earth. And in the distance, 2 more stars would shine, bright beacons in an alien sky. The moon's thin atmosphere might glow with auroras as charged particles from the multiple stars interact with its magnetic field. Beneath the ice, in dark, pressurized oceans, hydrothermal vents could provide energy for chemosynthetic life. Organisms that derive energy not from sunlight, but from chemical reactions. We're learning that life finds a way in the most unexpected places. If moons around PH1 exist, they'd be among the most exotic, potentially habitable environments we know of. Confirming PH1's existence required detective work of the highest order. The primary technique, transit photometry, gives us the planet's size and orbital period. But to measure its mass, astronomers turn to radial velocity spectroscopy. As PH1 orbits, its gravity tugs on its parent stars, causing them to wobble ever so slightly. By measuring the Doppler shift in the star's light, how their spectral lines shift toward blue and red, astronomers can calculate the planet's mass. The challenge with PH1 is that we're not dealing with one star wobbling, but two stars orbiting each other, both wobbling due to the planet. Disentangling those signals required sophisticated computer modeling. Even after confirmation, mysteries remain. We don't know PH1's exact mass with high precision. We haven't characterized its atmosphere. At 5,000 light-years away, the planet is too distant and too small for current instruments to perform detailed spectroscopy. Future observations with the James Webb Space Telescope or next-generation extremely large telescopes might change that. They could potentially detect the chemical signatures of molecules in PH1's atmosphere, or even spot large moons through tiny timing variations in the transits. But perhaps the greatest mystery is formation. How exactly did PH1 come to be? Did it form where it is now, somehow cobbling together material in that chaotic circumbinary environment? Or did it form farther out in a calmer region, then migrate inward? We're still working on the answer. PH1 is more than a curiosity. It's a teacher, expanding our understanding of what's possible in the universe. Before Kepler, we thought planetary systems would resemble our own. Rocky worlds close to the star, gas giants farther out, nice and orderly. Instead, we found hot Jupiters orbiting in days, super-Earths with no analog in our system, rogue planets drifting through interstellar space, and circumbinary worlds like PH1. Every time we think we understand planetary formation, the universe surprises us. PH1 tells us that planets can form in environments far more extreme than we imagined. And that has profound implications. Half of all stars in our galaxy exist in binary or multiple systems. If circumbinary planets are common, the total number of planets in the Milky Way could be far higher than estimates based solely on single-star systems. More planets means more chances for life, more potential destinations for humanity's future exploration, more opportunities to understand the cosmic conditions that allow worlds, and perhaps civilizations, to arise. But perhaps the most important lesson of PH1 isn't about planets at all. It's about people. I'm not a professional astronomer. I'm just someone who loves space. The fact that I could contribute, that I could help discover a planet, it's incredible. It shows that science isn't just for people in universities. It's for everyone. Since PH1, citizen scientists have discovered dozens of exoplanets. They've identified stellar flares, asteroid occultations, even potentially habitable worlds. The partnership between professional astronomers and enthusiastic amateurs has become a model for modern research. When you look at data from space, you're seeing photons that traveled thousands of years to reach us. You're touching the universe in a very real way. And sometimes, if you're lucky and patient, you find something no one has ever seen before. The story of PH1 inspires a new generation. It tells them that discovery is still possible, that the universe still holds secrets, and that anyone with curiosity and dedication can contribute to our understanding of the cosmos. 5,000 light-years from Earth, PH1 continues its eternal dance around two suns, watched over by two more stars in the distance. It doesn't know it's remarkable. It doesn't know that across the vast gulf of space, a small blue world orbiting an ordinary yellow star has discovered it, studied it, marveled at it. PH1 is one planet, one world among billions in our galaxy, trillions in the observable universe. Each one is unique. Each one has a story written in its orbit, its composition, its history. And each discovery brings us closer to understanding our place in this magnificent, mysterious cosmos. We're no longer alone in wondering about other worlds. We have found them. We're studying them. And in doing so, we are answering the oldest questions humanity has ever asked. What else is out there? And could life, in some form we might not yet imagine, exist beyond our pale blue dot? The hunt continues. The discoveries multiply. And every night, new citizen scientists sit down at their computers, examining light from distant stars, searching for that telltale dip, the signature of another world. Perhaps tonight, someone will find the next PH1, another impossible world, waiting to teach us just how little we truly know and how much there is yet to discover. Things are about to heat up fast with the next planet on our list, WASP 30b, the Inferno world. In the constellation Aquarius, the water-bearer, 1,200 light-years from Earth, orbits a world that defies imagination. A planet where the surface temperature could melt rock, where winds howl at thousands of miles per hour, where clouds of vaporized iron and silicate minerals rain down like burning snow. This is WASP 30b, a hot Jupiter, an inferno world, a laboratory for understanding the most extreme planetary environments in our galaxy. Our story begins not with a single telescope, but with a coordinated network spanning 2 hemispheres. The wide-angle search for planets, WASP, represents one of the most successful ground-based exoplanet hunting programs ever conceived. WASP was designed with a specific goal: find planets by watching them cross in front of their host stars. We call this the transit method. When a planet passes between us and its star, it blocks a tiny fraction of the star's light, maybe 1%, maybe less. Our cameras photograph the entire sky every few minutes, all night, every clear night. We're not looking for needles in haystacks. We're looking for needles in fields of haystacks. WASP consists of 2 robotic observatories, WASP North in La Palma and WASP South in South Africa. Together, they can observe the entire sky, detecting planetary transits with remarkable efficiency. Each camera has a field of view covering hundreds of square degrees, roughly 1,000 full moons worth of sky in a single exposure. But detection is only the first step. Each candidate's signal must be confirmed through follow-up observations using larger telescopes and more precise instruments. In May 2010, the WASP team announced the discovery of WASP 30b, along with several other exoplanets found in their systematic survey. The planet was detected through repeated transits observed over multiple observing seasons. What immediately caught our attention about WASP 30b was the clarity of the transit signal. The star, WASP 30, cataloged as 1 SWASP J 2316 17.33-014137.9, is relatively bright, with a visual magnitude of 12.2. That's faint by standards, but bright enough for detailed follow-up studies. The transits were deep, regular, occurring every 4.16 days. This told us we were looking at a large planet in a very close orbit. But a transit tells you only so much. It reveals the planet's size and orbital period, but not its mass. To determine mass, and thereby understand what kind of world this truly was, the team needed radial velocity measurements. We used the Corley spectrograph to measure the star's radial velocity, how fast it's moving toward or away from us. When a planet orbits, it tugs on its star, causing the star to wobble. By measuring the Doppler shift in the star's spectral lines, we can determine this wobble's amplitude, and from that, calculate the planet's mass. The measurements revealed a planet with a mass approximately 0.6 times that of Jupiter, roughly 60% of Jupiter's mass, or about 190 Earth masses. Combined with the transit data showing a radius 1.25 times Jupiter's, the team could calculate WASP-30b's density. And that density was surprisingly low, about 0.32 grams per cubic centimeter, less than half of Jupiter's density. This is a puffy, inflated world, its atmosphere bloated by intense stellar radiation. To understand WASP-30b, we must first understand its star. WASP-30 is an F8 type dwarf star, slightly hotter, slightly more massive, and slightly brighter than our Sun. WASP-30 has a mass about 1.2 times that of the Sun and is roughly 1.3 times as large. Its effective temperature is around 6,200 Kelvin compared to the Sun's 5,800. That might not sound like much, but means WASP-30 emits significantly more radiation, about 1.6 times the Sun's luminosity. The star's age is estimated at approximately 1 to 2 billion years, relatively young compared to our 4.6 billion-year-old Sun day. Its metallicity, the abundance of elements heavier than hydrogen and helium, is slightly higher than solar, supporting the planet formation theory that giant planets form more readily around metal-rich stars. Located 1,200 light-years away in Aquarius, WASP-30 is far beyond naked-eye visibility but easily accessible to modern telescopes. Its relative brightness and the large size of WASP-30b's transits make this system ideal for detailed study, a cosmic laboratory delivered to our doorstep. After months of follow-up observations, we had enough data to confirm WASP-30b as a genuine exoplanet. We published our findings in the peer-reviewed journal Astronomy and Astrophysics in 2011. The planet joined the growing catalog of hot Jupiters discovered by WASP, a catalog that now includes over 200 confirmed planets. But discovery is just the beginning. The real work, understanding what WASP-30b is, how it formed, what its atmosphere contains, and what it tells us about planetary physics, was only just starting. In our solar system, Jupiter orbits at an average distance of 778 million kilometers from the Sun, 5 times farther than Earth. Its year lasts nearly 12 Earth years. But WASP-30b exists in a radically different configuration. WASP-30b orbits just 0.0475 astronomical units from its star. That's 7.1 million kilometers, only 11% of Mercury's distance from our Sun. At this proximity, WASP-30b completes one orbit every 4.16 days. An entire year on this world lasts less than a single Earth week. Hot Jupiters completely upended our understanding of planetary systems when they were first discovered in the 1990s. According to our formation theories, giant planets should form in the cold outer regions of protoplanetary disks, where ice and gas are abundant. Yet here we find Jupiter-sized worlds practically skimming their star surfaces. These planets are not just unusual. They're fundamentally challenging our models of how planetary systems evolve. The defining characteristic of WASP-30b is heat, unrelenting, overwhelming, inconceivable heat. Based on the planet's distance from its star and the star's luminosity, we can calculate the equilibrium temperature, the temperature the planet would reach if it perfectly absorbed and redistributed stellar radiation. For WASP-30b, assuming an albedo similar to Jupiter's and efficient heat redistribution, the equilibrium temperature is approximately 1,500 Kelvin. That's roughly 1,200 degrees Celsius or 2,200 degrees Fahrenheit. To put this in perspective, iron melts at 1,538 degrees Celsius. Gold melts at 1,064 degrees. WASP-30b's atmosphere is hot enough to keep most metals molten, but the actual temperature distribution is likely far more complex. Hot Jupiters are believed to be tidally locked, with one hemisphere permanently facing the star, the day side, and the other in eternal night, the night side. The day-night temperature contrast depends on atmospheric circulation. If winds efficiently redistribute heat from the day side to the night side, temperatures might be more uniform. But if circulation is inefficient, the day side could be significantly hotter, perhaps 2,500 Kelvin, while the night side remains relatively cool at 800 to 1,000 Kelvin. This creates a temperature gradient of over 1,500 degrees across the planet, the most extreme weather patterns imaginable. What does WASP-30b's atmosphere contain? At these temperatures, the chemistry becomes exotic. Like Jupiter, WASP-30b's atmosphere is primarily hydrogen and helium, the most abundant elements in the universe. But the intense heat fundamentally alters the chemistry. At temperatures above 1,000 Kelvin, molecules that would normally be stable, like water, methane, and ammonia, break apart or exist in unusual chemical states. The primary components are hydrogen and helium, making up roughly 90% and 10% of the atmosphere by mass, respectively. There is also water vapor present in trace amounts, but at these temperatures, water remains gaseous and possibly dissociated into hydrogen and oxygen radicals. The carbon monoxide level is stable at high temperatures and likely abundant. Carbon monoxide dominates over methane in hot atmospheres. If titanium oxide, TiO, and vanadium oxide, VO, are present, these molecules can create temperature inversions, where the upper atmosphere is hotter than the lower layers by absorbing stellar ultraviolet and visible light. Sodium, Na, potassium, K, iron, Fe, and magnesium, Mg, exist as individual atoms or ions, creating broad absorption features in the planet spectrum. In the cooler regions of the night side or upper atmosphere, silicon and iron compounds may condense into clouds, not water clouds, but clouds of minerals. The dayside atmosphere may contain little to no condensed material. Everything remains gaseous. But as atmospheric gases circulate to the night side and cool, we may see exotic cloud formation. Instead of water, ice, or ammonia crystals, we're talking about clouds of corundum, the mineral that forms rubies and sapphires, or clouds of iron, magnesium silicates, even molten droplets of rock. If you could survive long enough to observe WASP-30b's weather, which you couldn't, what would you see? Our circulation models suggest that hot Jupiters develop powerful equatorial jet streams, eastward flowing winds at velocities potentially exceeding several kilometers per second. That's fast in sound. Supersonic winds. These jets arise from the extreme heating on the day side, which creates massive pressure gradients driving air toward the night side. These winds don't just redistribute heat. They transport chemical species, create shear zones, generate storms, potentially dwarfing Jupiter's Great Red Spot. At the terminator, the boundary between day and night, temperatures plunge, potentially triggering dramatic condensation events. Imagine standing at the terminator. On one side, the star's radiation is so intense you'd be vaporized instantly. On the other, eternal twilight, where the temperature is merely hot enough to melt lead. Between them, winds rage with the force of 1,000 hurricanes, carrying clouds of vaporized minerals. Lightning on hot Jupiters could be extraordinarily common and powerful. The rapid circulation, temperature gradients, and chemical activity all contribute to electrical charging. We're not talking about Earth-style thunderstorms. We're talking about electrical discharges orders of magnitude more energetic, possibly affecting the entire atmospheric column. WASP-30b's orbit is nearly circular, with an eccentricity less than 0.02, virtually a perfect circle. But the tidal forces at play are profound. At such close range, tidal forces from the star are immense. These forces have almost certainly locked WASP-30b into synchronous rotation. One side always faces the star. The same mechanism that locks our moon to Earth is operating here, but far more powerfully. The tidal bulge raised on WASP 30b by its star is enormous, potentially distorting the planet's shape noticeably. The planet's rotation period matches its orbital period, 4.16 days. This synchronous rotation creates the permanent day and night sides, fundamentally shaping the planet's climate and atmospheric dynamics. But there's another consequence of this proximity. WASP 30b is slowly losing atmosphere. The intense stellar radiation heats the upper atmosphere to such high temperatures that hydrogen and helium atoms gain enough energy to escape the planet's gravity entirely. Hot Jupiters can lose mass through hydrodynamic escape. Essentially, the atmosphere boils off into space. The rate depends on the planet's mass, the stellar radiation intensity, and the atmospheric composition. For a planet like WASP 30b, mass loss rates are estimated at millions to tens of millions of kilograms per second. Enormous on human scales, but the planet is so massive that it would take billions of years to lose a significant fraction of its mass. How do we study a world 1,200 light-years away? How can we measure its size, mass, atmospheric composition, and temperature when we cannot see it directly? The answer lies in precision and patience. The transit method is beautifully simple in principle. When WASP 30b crosses in front of its star from our perspective, it blocks approximately 1.5% of the star's light. By measuring the amount of light blocked and the duration of the transit, we can calculate the planet's radius relative to the star's radius. And because we know the star's size from spectroscopic observations, we can determine the planet's absolute size. The transit of WASP 30b lasts approximately 2.5 hours, the time it takes the planet to move completely across the star's disk. But the transit provides more information than just size. The exact shape of the light curve, how quickly the light dims at ingress when the planet begins crossing, and egress when it finishes, tells us about the planet's orbital inclination and the star's limb darkening, the phenomenon where a star appears dimmer at its edges than at its center. Observing multiple transits over months or years allows us to refine our measurements with extraordinary precision. For WASP 30b, the orbital period is known to within a fraction of a second, 4.156775 plus or minus 0.000008 days. That precision comes from timing hundreds of transits and watching for any variations that might indicate additional planets, moons, or orbital precession. While transits reveal size, radial velocity measurements reveal mass. This technique exploits the Doppler effect, the same phenomenon that changes the pitch of a passing ambulance's siren. WASP 30 moves toward and away from us at velocities of approximately 65 meters per second due to WASP 30b's gravitational pull. This is faster than a speeding bullet, but incredibly slow on astronomical scales. To measure these velocities, we use high-resolution spectrographs like Coralie, which can detect Doppler shifts corresponding to velocity changes of just a few meters per second, about the speed of a brisk walk. By measuring this velocity variation and combining it with the orbital period from transits, astronomers calculated WASP 30b's mass, approximately 0.6 Jupiter masses, or about 190 Earth masses. Together, mass and radius give us density, and density tells us about composition and internal structure. WASP 30b's low density of 0.32 grams per cubic centimeter indicates a largely gaseous composition with significant atmospheric inflation due to heating. The ultimate goal is atmospheric characterization, determining what molecules and atoms exist in WASP 30b's atmosphere. This requires transmission spectroscopy. During a transit, starlight passes through the planet's atmosphere before reaching us. Different molecules absorb light at specific wavelengths. Sodium absorbs yellow light, water vapor absorbs in the infrared, and so on. By comparing the spectrum of the star during transit to the spectrum when the planet isn't transiting, we can identify absorption features caused by the planet's atmosphere. This technique has been used successfully on many hot Jupiters, revealing sodium, potassium, water vapor, and even molecules like titanium oxide. While comprehensive transmission spectroscopy of WASP-30b has not yet been published extensively, the planet's brightness and large atmospheric scale height make it an excellent target for future observations. With the James Webb Space Telescope, we can observe an unprecedented detail across infrared wavelengths where many molecular signatures are strongest. For a planet like WASP-30b, JWST could detect water, carbon monoxide, methane or its absence, metal oxides, and potentially even signatures of complex chemistry or cloud formation. Each spectrum is like a chemical fingerprint of the atmosphere. There's another powerful technique, secondary eclipse observations. When WASP-30b passes behind its star, when it's eclipsed from our view, the total light from the system drops slightly because we lose the planet's thermal emission. By measuring the depth of the secondary eclipse at different wavelengths, we can determine the planet's thermal emission spectrum, essentially its temperature and how it varies with wavelength. This tells us not just how hot the planet is, but also what's in the atmosphere and how efficiently heat is redistributed from day to night. For hot Jupiters like WASP-30b, secondary eclipses can reveal whether the day side has a temperature inversion, whether clouds form, and whether the chemistry matches our models. Additionally, by observing the planet's brightness as it orbits, a technique called phase curve photometry, astronomers can map temperature variations across the planet's surface, pinpointing the hottest region, the day-night temperature difference, and the presence of reflective clouds. Studying exoplanets is not easy. At 1,200 light-years, WASP-30b is 1 trillion kilometers away, so distant that light itself takes more than a millennium to reach us. Every photon we collect is ancient history. The signals we're measuring are astonishingly small. A 1.5% transit depth means we're detecting a brightness change of 0.015 magnitudes, barely perceptible even with sensitive instruments. Radial velocity measurements of 65 meters per second correspond to Doppler shifts of a few parts in 10 million. Atmospheric absorption features might change the transit depth by a few parts in 10,000. This requires extraordinary instrumental precision and careful data analysis. Then there are systematic errors, atmospheric turbulence blurring ground-based observations, instrumental drift, star spots on the host star mimicking planetary signals. Each of these must be accounted for and corrected. Studying exoplanets is as much about patience and persistence as it is about technology. We observe the same target night after night, season after season, accumulating photons, building signal-to-noise. We refine our models, test hypotheses, compare predictions to data. It's painstaking work, but each improvement brings us closer to truly understanding these distant worlds. How did WASP-30b come to be? The answer takes us back billions of years to the birth of the WASP-30 system. Stars form from collapsing clouds of gas and dust. As they collapse, conservation of angular momentum causes them to spin up and flatten into disks. These protoplanetary disks are where planets are born. In the cold outer regions, beyond what we call the ice line, temperatures are low enough for water and other volatiles to condense into solid ice. This dramatically increases the amount of solid material available for planet building. According to the core accretion model, giant planets form when a solid core of rock and ice, perhaps 10 to 15 Earth masses, grows large enough to gravitationally capture massive envelopes of hydrogen and helium gas from the surrounding disk. This process is efficient in the cold outer disk, but very slow in the hot inner regions. Yet 30b orbits just 7 million kilometers from its star, far inside where any ice could exist, far inside where giant planets should form. This paradox troubled astronomers when the first hot Jupiters were discovered in the 1990s. The solution is planetary migration. WASP. 30b didn't form where we see it today. It formed much farther out, perhaps several astronomical units from its star, and then migrated inward. There are two main mechanisms for this: disk migration and dynamical interactions. When a giant planet forms, it creates spiral density waves in the protoplanetary disk, like the wake behind a boat. These waves exert torques on the planet, causing it to lose angular momentum and spiral inward. This process, called Type 2 migration, can move Jupiter-mass planets from $5 down to 5 cents in less than 1 million years. Very fast on astronomical timescales, but slow compared to the planet's orbital period. Alternatively, WASP 30b might have migrated through gravitational interactions with other planets or stellar companions. If the system initially contained multiple giant planets on eccentric orbits, close encounters could have scattered one planet inward while ejecting others. Or if WASP 30 were in a binary star system earlier in its history, the Kozylitiv mechanism, where the binary companion tilts and stretches a planet's orbit, could have brought WASP 30b closer to its star. Tidal forces would then circularize the orbit, resulting in the hot Jupiter configuration we see today. One of WASP 30b's most intriguing properties is its load density, 0.32 grams per cubic centimeter. For comparison, Jupiter's density is 1.33, and even Saturn, the least dense planet in our solar system, has a density of 0.69. WASP 30b is inflated well beyond what simple models predict. Hot Jupiters are generally more inflated than cold gas giants, but the degree of inflation varies. Some hot Jupiters are only slightly larger than Jupiter. Others, like WASP 30b, are significantly puffier. The leading explanation involves energy deposition in the planet's interior. Intense stellar radiation heats the upper atmosphere, but somehow energy must be transported deep into the planet to prevent the interior from contracting under its own gravity. Several mechanisms have been proposed: downward transport of kinetic energy from atmospheric winds, ohmic dissipation caused by electrical currents interacting with magnetic fields, or enhanced opacity in the atmosphere trapping heat. No single mechanism fully explains all observations, suggesting multiple processes may be at work simultaneously. Understanding atmospheric inflation is crucial not just for explaining WASP 30b, but for testing our theories of planetary interiors, atmospheric dynamics, and energy transport. These planets are natural laboratories for extreme physics that we can't replicate on Earth. WASP 30b is one among hundreds of known hot Jupiters. These planets are rare, occurring around only 0.5 to 1% of Sun-like stars, but their very existence has revolutionized planetary science. Hot Jupiters forced us to abandon the idea that our solar system is typical. They showed us that planets can migrate, that planetary systems can be dynamically violent, and that diversity is the rule rather than the exception. They also serve as test beds for atmospheric characterization techniques that will eventually apply to smaller, potentially habitable planets. Each hot Jupiter has its own story. Some, like WASP 12b, are so close to their stars that they're being tidally shredded, losing mass faster than WASP 30b. Others, like KLT 9b, orbit even hotter stars and reach dayside temperatures exceeding 4,000 Kelvin, hot enough to dissociate molecular hydrogen into atomic hydrogen. WASP 30b sits in the middle of this distribution, extreme by Earth standards, but representative of the broader hot Jupiter population. Its moderate temperature, large radius, and bright host star make it an ideal target for comparative studies. The James Webb Space Telescope, launched in December 2021, represents a quantum leap in our ability to study exoplanet atmospheres. With its 6.5-meter mirror and suite of infrared instruments, JWST can observe atmospheric features that previous telescopes could barely detect. JWST is purpose-built for atmospheric characterization. Its infrared sensitivity allows us to detect molecules like water, carbon dioxide, methane, and ammonia with unprecedented precision. For a planet like WASP-30b, we can measure not just what's in the atmosphere, but its abundance, its vertical distribution, and how it varies between day and night. We can test whether our chemical models are correct and whether there are unexpected species we haven't predicted. JWST has already observed dozens of exoplanets, revealing atmospheric compositions, temperature structures, and even detecting molecules like sulfur dioxide that weren't expected. WASP-30b, with its favorable properties, is an excellent candidate for JWST observation programs. Space telescopes aren't the only tools advancing exoplanet science. On Earth, a new generation of extremely large telescopes is under construction. The next generation ground-based telescopes, the extremely large telescope with its 39-meter mirror, the 30-meter telescope, and the giant Magellan telescope, will have light-collecting power far exceeding anything we have today. Combined with adaptive optic systems to correct for atmospheric turbulence, these telescopes will achieve spectroscopic precision rivaling space telescopes for bright targets like WASP-30b. These facilities will enable high-resolution spectroscopy, potentially detecting individual spectral lines from molecules, measuring wind velocities through Doppler shifts, and even mapping temperature and chemical variations across the planet's disk using a technique called Doppler tomography. For all we've learned about WASP-30b, profound mysteries remain. Some hot Jupiters show stratospheric inversions where the upper atmosphere is hotter than lower layers, likely due to absorption by titanium oxide or vanadium oxide. Does WASP-30b have this? Spectroscopic observations can answer this by measuring how temperature varies with altitude. Phase curve observations measuring brightness variations as the planet orbits can reveal how efficiently winds transport heat from the day side to the night side. This tests atmospheric circulation models and constrains wind speeds and patterns. Cloud formation depends on temperature and chemistry. Spectroscopic observations can reveal whether clouds of silicates, iron, or corundum exist and where they condense on the cooler night side, at the terminator, or in the upper atmosphere. Magnetic fields play roles in atmospheric dynamics, energy transport, and aurora generation. Radio observations or detailed modeling of atmospheric circulation could constrain WASP-30b's magnetic field, if it exists. Does WASP-30b have a solid core of rock and ice, or is it entirely gaseous? How much heavy element enrichment exists? These questions are harder to answer, but can be addressed through detailed comparisons of mass, radius, and atmospheric composition. Hot Jupiters like WASP-30b teach us that planetary systems are dynamic, evolving entities. Planets can migrate vast distances. They can undergo dramatic atmospheric changes. Their properties depend not just on their mass and composition, but on their entire evolutionary history, where they formed, how they migrated, how they interact with their stars. These lessons extend to all planetary science, including the search for habitable worlds. Understanding atmospheric chemistry on hot Jupiters informs our models of atmospheric chemistry on smaller planets. Understanding migration helps us predict whether Earth-like planets in a habitable zone are common or rare. Understanding energy transport helps us model climates on diverse worlds. WASP-30b will never host life. It's a realm of extremes utterly hostile to biology as we know it. But in studying this inferno world, we gain the knowledge and tools to explore other worlds. Worlds where temperatures are moderate, where atmospheres are stable, where liquid water might pool on solid surfaces. Each hot Jupiter is a stepping stone toward the ultimate goal, finding another Earth. WASP 30b orbits in silence, as it has for billions of years, as it will for billions more. No one will ever stand on its surface, because it has no surface. No spacecraft will ever land there. The crushing pressures and searing heat would destroy any probe in seconds. No human eye will ever witness its alien sunrises or its raging storms. And yet we know it. We know its size, its mass, its orbit. We know its temperature, its composition, its history. We know it as surely as we know our own world. Not through touch or sight, but through light and mathematics, through patience and ingenuity. Every exoplanet discovery is a victory, not just for science, but for human curiosity. We look at the stars and wonder what's there. And now we have answers. We've discovered thousands of worlds, each one unique, each one expanding our understanding of what's possible in the universe. The story of WASP 30b is far from over. Future observations will refine our understanding, reveal new details, challenge old assumptions. Perhaps one day, we'll detect moons orbiting this giant, worlds that, despite the harsh environment, could harbor exotic forms of chemistry or even, conceivably, some strange form of life. But even if WASP 30b remains forever lifeless, it matters. It teaches us about planetary formation, atmospheric dynamics, the diversity of worlds. It reminds us that the universe is stranger, richer, more varied than we ever imagined. On a clear night, if you know where to look, you can see the constellation Aquarius low on the horizon. Among its faint stars shines WASP 30, too dim for the naked eye, but they're nonetheless. And orbiting that star, every 4.16 days, WASP 30b completes another journey around its inferno world. It's waiting for us, waiting for our next generation of telescopes, our next observing campaign, our next breakthrough, waiting to reveal its secrets one photon at a time. This is WASP 30b, an inferno world, a hot Jupiter, a laboratory of extremes, a testament to the power of human curiosity. And out there, in the vast expanse of space, thousands more worlds await discovery, each one with its own story, each one waiting to teach us something new about the universe we inhabit. The search continues. The questions multiply. And the universe, as always, surprises us. Now let's take a deep dive into one of my personal favorites. TESS Object of Interest, or TOI, 1785.01, and humanity's quest for new worlds. Every 3.2 days, something extraordinary happens 172 light-years from Earth. A world, possibly rocky, possibly ocean-covered, possibly teeming with the chemistry of life, passes in front of its star. For just a few hours, it blocks a tiny fraction of starlight, creating a signal so subtle that only the most sophisticated instruments can detect it. This is TOI 1785.01, a candidate exoplanet discovered by NASA's Transiting Exoplanet Survey satellite, an object of intense interest to astronomers searching for habitable worlds, a mystery waiting to be solved. This is the story of how we found it, how we're studying it, and what it might teach us about the possibility of life beyond Earth. At 6:51 p.m. Eastern Time on April 18, 2018, a SpaceX Falcon 9 rocket lifted off from Cape Canaveral, carrying a spacecraft that would revolutionize the search for exoplanets. Its name, TESS, the Transiting Exoplanet Survey Satellite. TESS was designed with a specific mission: survey 85% of the sky, monitoring more than 200,000 of the brightest stars near Earth, searching for planets through the transit method. It's a follow-up to NASA's Kepler mission, but with a crucial difference. TESS focuses on nearby, bright stars that are perfect for detailed follow-up studies. TESS orbits Earth in a path engineered for efficiency and stability. Every 13.7 days, it completes one orbit, spending most of its time far from Earth to avoid interference. Its 4 wide-field cameras collectively observe a 24 by 96-degree strip of sky for 27 days before moving to the next sector. In 2 years, TESS surveys nearly the entire sky, creating the most comprehensive census of nearby exoplanets ever attempted. What makes TESS special is accessibility. Kepler found thousands of planets, but many orbit faint, distant stars that are difficult to study further. TESS finds planets around bright stars, stars we can observe with ground-based telescopes, with the Hubble Space Telescope, with the James Webb Space Telescope. These are the systems where we can measure masses, characterize atmospheres, and search for signs of habitability. TESS uses a technique called transit photometry, the same method pioneered by Kepler. The principle is elegant. When a planet crosses in front of its star from our perspective, it blocks a small fraction of the star's light, creating a dip in brightness. The depth of the transit tells us the planet's size relative to its star. The duration tells us about the planet's orbital speed and distance. The period, how often the transit repeats, tells us the length of the planet's year. From these 3 pieces of information, combined with knowledge about the host star, we can determine the planet's radius, orbital period, and distance from its star. But detecting these transits is extraordinarily challenging. For an Earth-sized planet orbiting a Sun-like star, the brightness dip is less than 0.01%, 1 part in 10,000. TESS must measure stellar brightness with exceptional precision, accounting for instrumental noise, cosmic rays, stellar variability, and countless other factors that could mimic a planetary signal. Every 30 minutes, TESS takes a full-frame image of its field of view. 4 priority stars, about 200,000 of the brightest and most interesting. It records brightness measurements every 2 minutes. That's over 21,000 data points per star per sector. Our algorithms search these light curves for the characteristic shape of a transit, a smooth, symmetric dip that repeats with clockwork regularity. In 2020, during TESS's analysis of Sector 15 observations, the automated planet-hunting algorithms detected something intriguing around a star cataloged as Teach C2-426-44328, a star later designated TOI 1785. When a candidate is detected, we call it a TESS Object of Interest, or TOI. TOI 1785.01 was the first candidate detected around this star, hence the .01 designation. The .01 means it's the first candidate. If we found additional planets in the system, they'd be numbered .02, .03, and so on. The initial data was promising. TOI 1785.01 appeared to be a super-Earth or sub-Neptune, a planet larger than Earth but smaller than Neptune, completing one orbit every 3.2 days. But detection is only the first step. Confirming that a transit signal is genuinely caused by a planet, rather than a false positive like an eclipsing binary star or instrumental artifact, requires extensive follow-up observations. For every 10 candidates TESS detects, maybe 8 turn out to be real planets. The rest are false positives, background eclipsing binaries, stellar activity, or other astrophysical phenomena that mimic transits. Our job is to separate the signal from the noise, the planets from the imposters. To understand TOI 1785.01, we must first understand its star. TOI 1785 is a K-type dwarf star, smaller, cooler, and dimmer than our Sun, but more massive and luminous than the smallest M-type red dwarfs. K-type stars are particularly interesting for habitability studies. They're cooler than Sun-like stars, which means they're habitable zones. The regions where liquid water could exist on a planet's surface are closer in. They're more stable than M dwarfs, which can produce violent flares that might strip away planetary atmospheres. And they live for tens of billions of years, potentially giving life more time to evolve than on planets around sun-like stars. TOI 1785's relative brightness and proximity make it an ideal target for follow-up observations. Unlike many Kepler discoveries thousands of light-years away, TOI 1785 is close enough that astronomers can obtain detailed spectra, measure stellar activity, and search for additional planets using ground-based telescopes. From TESS's transit observations, we can derive fundamental properties of TOI 1785.01. But each measurement comes with uncertainties, and some properties can only be estimated until follow-up observations provide more data. Based on the depth of the transit and our understanding of the host star size, we estimate TOI 1785.01 has a radius of approximately 1.5 to 2.5 Earth radii. This places it in the super-Earth to sub-Neptune category, larger than Earth, but smaller than Uranus or Neptune. This size range is particularly interesting because nothing like it exists in our solar system. The orbital distance is a crucial factor. At 4 cents, TOI 1785.01 orbits nearly 13 times closer to its star than Earth does to the Sun. But because TOI 1785 is cooler and less luminous than the Sun, the planet receives far less radiation than you might expect. The equilibrium temperature, the temperature a planet would reach if it perfectly absorbed and redistributed stellar radiation, is estimated around 700 Kelvin or about 427 degrees Celsius. That's hot by Earth standards, hotter than Venus, but not as extreme as the 1,500 to 2,000 Kelvin temperatures we see on hot Jupiters. The planet is too hot for liquid water on its surface, so it's not in the habitable zone. But it's cool enough that its atmosphere, if it has one, might be interesting. Planets between 1.5 and 2.5 Earth radii occupy a fascinating and poorly understood region of the exoplanet size distribution. Some are rocky super-Earths with thick atmospheres. Others are mini-Neptunes, small gas planets dominated by hydrogen and helium. Still others might be ocean worlds or planets with exotic compositions. This is one of the most important questions in exoplanet science, the super-Earth/sub-Neptune transition. We've observed that planets smaller than about 1.5 Earth radii tend to be rocky, like Earth and Mars. Planets larger than about 2 Earth radii often have thick hydrogen-helium atmospheres, like Neptune. But there's a gap in between, a region where we're not sure what dominates. Understanding this transition helps us predict planetary compositions and formation histories. For TOI 1785.01, determining whether it's a rocky super-Earth or a gaseous mini-Neptune requires measuring its mass. Mass combined with radius gives density, and density reveals composition. To measure TOI 1785.01's mass, astronomers turn to the radial velocity method, also called the Doppler wobble technique. When a planet orbits a star, it doesn't just revolve around a stationary point. Both planet and star orbit their common center of mass. For a Jupiter-mass planet, this causes the star to wobble at tens to hundreds of meters per second. For an Earth-mass planet, the wobble might be just a meter per second, the speed of a leisurely walk. We detect this wobble by measuring the Doppler shift in the star's spectral lines. Radial velocity measurements of TOI 1785 have likely been attempted or are ongoing, but as of the available data, a precise mass measurement has not been published. This is common for newly discovered candidates. Confirmation and characterization can take months to years, depending on observing time availability and the planet's properties. Measuring the mass of a small planet around a relatively faint star is challenging. We need multiple observations spread over several orbital periods to build up signal-to-noise. We need to account for stellar activity, star spots, flares, convection that can mimic or mask planetary signals. For a planet with a 3.2-day period, we need at least a few weeks of observations, and often months, to confidently determine the mass. One of the most exciting aspects of TOI 1785.01 is its potential for atmospheric characterization. If the planet has an atmosphere, and depending on its composition, future observations could reveal its chemical makeup. For atmospheric studies, we use transmission spectroscopy. During a transit, some starlight passes through the planet's atmosphere before reaching us. Different molecules absorb light at specific wavelengths: water vapor in the infrared, methane at other wavelengths, carbon dioxide, sodium, potassium. By comparing the spectrum during transit to the spectrum outside of transit, we can identify which molecules are present. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is revolutionizing atmospheric studies of exoplanets. For a planet like TOI 1785.01, JWST could potentially detect so many useful things, such as water vapor, carbon dioxide, methane, ammonia, hydrogen sulfide, sodium, potassium, and much more. The presence or absence of certain molecules tells us about the planet's formation, its temperature structure, its chemistry. For instance, a thick hydrogen atmosphere would suggest a mini-Neptune. A thin atmosphere dominated by carbon dioxide might indicate a rocky world with volcanism. A water-rich atmosphere could point to an ocean world. Each possibility teaches us something new about planetary diversity. A transit-like curve is deceptively simple, a flat baseline punctuated by periodic dips. But encoded in that curve is a wealth of information about the planet and its orbit. The depth of the transit tells us the planet's size. If the planet blocks 1% of the star's light, the planet's cross-sectional area is 1% of the star's. From there, we calculate the planet's radius. The duration of the transit depends on the planet's orbital speed and where it crosses relative to the star's center. A planet crossing centrally will have a longer transit than one crossing near the limb. But there's more. The shape of the transit, how quickly the brightness dims at the beginning, ingress, and how quickly it recovers at the end, egress, is affected by limb darkening, the phenomenon where stars appear dimmer at their edges than at their centers. Limb darkening creates a curved, U-shaped transit rather than a flat-bottomed one. By modeling this shape, we can infer properties of the star's atmosphere and improve our measurement of the planet's size. We can also search for deviations from the expected shape, bumps or wiggles that might indicate additional planets, moons, rings, or even star spots. One of the most exciting possibilities is that TOI 1785.01 is not alone. Many exoplanetary systems contain multiple planets, and TESS is designed to find them. When analyzing TOI 1785, we search not just for the known candidate, but for additional transit signals that might have been too faint or occurred at the wrong time to trigger the initial detection algorithm. Multi-planet systems are incredibly valuable for understanding planetary formation and dynamics. If TOI 1785.01 has siblings, other planets in the system, we can study how they interact, whether they're in resonance, whether their compositions correlate with their distances from the star. So far, only TOI 1785.01 has been announced. But absence of evidence is not evidence of absence. Additional planets might exist on longer period orbits that TESS hasn't observed for enough cycles, or they might not transit from our viewing angle. Radial velocity studies or extended TESS observations might reveal hidden companions. If additional planets exist, they might reveal themselves through a subtle effect called transit timing variations, or TTVs. In a single planet system, transits occur like clockwork, every 3.2 days, on schedule, forever. But if there are two or more planets, Their mutual gravitational interactions cause slight perturbations in their orbits. A transit might occur a few minutes early or late compared to the prediction. By measuring these timing variations over many transits, we can infer the presence, masses, and orbital properties of unseen planets. For TOI 1785.01, careful monitoring over many transits could reveal TTVs indicating additional planets. This technique has been used successfully to discover and characterize planets in multi-planet systems detected by Kepler. TOI 1785 is part of a special class of stars, K-type dwarfs, that are emerging as prime targets in the search for habitable worlds. K-dwarfs have several advantages. They're more common than Sun-like G-type stars, giving us more targets to study. They're more stable and less active than M-dwarfs, which produce frequent flares and high-energy radiation that could harm planetary atmospheres. And they live for 15 to 45 billion years, far longer than the Sun's 10 billion-year lifespan. If life needs time to evolve, K-dwarf systems might offer the most favorable conditions. TOI 1785.01 orbits too close for habitability, but its study helps us understand planets around K-dwarfs more broadly. Each discovery refines our models, informs our search strategies, and brings us closer to finding truly Earth-like worlds. TOI 1785.01 contributes to a larger picture, understanding the diversity and distribution of planets in our galaxy. We've now discovered over 5,000 confirmed exoplanets, with thousands more candidates. One of the most striking findings is how different exoplanetary systems are from our own solar system. We see hot Jupiters orbiting in days, super-Earths unlike anything we have, mini-Neptunes, and a bewildering variety of configurations. TOI 1785.01, as a super-Earth or sub-Neptune candidate around a K-dwarf, fits into this broader tapestry. One particularly intriguing feature of the exoplanet population is the radius gap, a relative scarcity of planets between 1.5 and 2 Earth radii, first identified by Caltech astronomer Benjamin Fulton. This gap suggests a fundamental division. Planets below the gap are predominantly rocky, while those above have substantial gaseous envelopes. The radius gap likely results from atmospheric loss. Planets that form with hydrogen-helium atmospheres either retain them and remain mini-Neptunes, or they lose them through stellar radiation and atmospheric escape, leaving behind a rocky core. TOI 1785.01, depending on its exact size, might be near this gap, making it especially valuable for understanding this transition. How do planets form around stars like TOI 1785? And why do we see the configurations we observe? Planets form from protoplanetary disks, rotating disks of gas and dust surrounding young stars. In the disk's cool outer regions, beyond the ice line, water and other volatiles freeze, allowing planets to grow larger by incorporating ice along with rock. Closer in, where TOI 1785.01 orbits, temperatures were too high for ice during formation. If TOI 1785.01 is a super-Earth, it likely formed from rock and metal. If it's a mini-Neptune, it might have formed farther out and migrated inward. Understanding where and how TOI 1785.01 formed requires measuring its composition, which requires knowing its mass and density. A dense planet suggests a rocky composition. A low-density planet indicates a significant volatile or gaseous component. While TOI 1785.01 itself is too hot for life as we know it, the techniques we developed studying planets like it paved the way for detecting biosignatures, signs of life, on more temperate worlds. A biosignature is something in a planet's atmosphere or on its surface that indicates the presence of life. On Earth, oxygen is a powerful biosignature. It's produced by photosynthesis and would disappear without life, continually replenishing it. Other potential biosignatures include methane in combination with oxygen, certain organic compounds, or even technosignatures, signs of technological civilizations. Detecting biosignatures requires exquisite precision. We must distinguish biological signals from geological or chemical processes that can mimic life. We must account for stellar activity, clouds, hazes, and countless other factors. Every planet we study, even those clearly uninhabitable, teaches us how to interpret spectra, model atmospheres, and refine our detection methods. TOI 1785.01 might not be the planet where we find life, but it's a stepping stone. It helps us understand planetary atmospheres, test our instruments, develop our techniques. When we finally observe a true Earth analog, a rocky planet in the habitable zone of a sun-like or K-dwarf star, we'll be ready because of all we've learned from planets like this. Confirming and characterizing TOI 1785.01 requires a global effort. Dozens of telescopes, operated by hundreds of astronomers, contribute observations. Ground-based follow-up is essential. We use transit observations from different sites to confirm the signal, rule out false positives, and refine the planet's properties. We use precision spectrographs to measure radial velocities and determine mass. We use photometric monitoring to search for additional transits or timing variations. It's a collaborative, international endeavor. The next frontier is atmospheric characterization, and for that, space-based observatories are essential. JWST is transforming exoplanet science. For a target like TOI 1785.01, we can observe transits in multiple infrared wavelengths simultaneously, detecting molecular absorption features with unprecedented sensitivity. We can also observe secondary eclipses when a planet passes behind the star to measure the planet's thermal emission and map its temperature. Whether TOI 1785.01 becomes a JWST target depends on several factors: its confirmed properties, competing priorities, and what initial characterization reveals. If the planet has an extended atmosphere or unusual composition, it could become a priority target. We're living in a golden age of exoplanet characterization. Every few weeks, new JWST results are published, detecting molecules, measuring atmospheric temperatures, even finding evidence for clouds and chemistry. Within the next decade, we'll have atmospheric spectra for dozens, perhaps hundreds of planets across a wide range of sizes, temperatures, and stellar environments. TESS is just the beginning. A new generation of missions will build on its discoveries, pushing deeper into the search for habitable worlds. The Nancy Grace Roman Space Telescope, launching in the late 2020s, will conduct exoplanet surveys using microlensing and direct imaging. The Habitable Worlds Observatory, planned for the 2040s, will directly image Earth-like planets, studying their atmospheres in detail. On the ground, extremely large telescopes with 30-meter class mirrors will achieve spectroscopic precision, allowing us to detect biosignature gases. Each generation of technology brings us closer to answering humanity's oldest question: are we alone? Planets like TOI 1785.01, discovered by TESS and characterized by follow-up observations, lay the groundwork for this quest. Every exoplanet is a natural laboratory, a place where nature has run an experiment we could never conduct ourselves. We have one data point for habitability: Earth. That's an extraordinarily limited sample size. By studying thousands of planets across a range of sizes, compositions, atmospheres, and stellar environments, we're expanding our understanding of what's possible. We're learning which planetary properties matter for habitability, which formation pathways lead to different outcomes, how planets evolve over time. TOI 1785.01 might not be habitable, but it teaches us about atmospheric retention, planetary composition, the effects of stellar radiation. These lessons inform our search for the next Earth, not just a planet that looks like Earth, but one that could support life. When I was a child, we didn't know if there were any planets beyond our solar system. Now, we know they're everywhere, probably more planets than stars in the galaxy. TESS is discovering worlds around nearby stars, worlds we could potentially visit with future technology, worlds where our descendants might someday stand. It's extraordinary. Every planet has a story. Every discovery is a piece of the cosmic puzzle. TOI 1785.01 is one candidate among thousands, but it matters. It might lead to new understanding. It might inspire a student to become a scientist. It reminds us that the universe is vast and full of wonders waiting to be explored. I love the designation TOI, TESS Object of Interest. It captures the excitement perfectly. These are objects of interest, mysteries to investigate, worlds that might teach us something profound. Every time we confirm a new planet, I feel that sense of discovery anew. We live in a remarkable time. For the first time in human history, we can answer the question, are there other worlds? The answer is yes, thousands of them, with more being discovered every month. But the deeper question remains, are there other worlds like ours? Places where water pools on solid surfaces, where atmospheres protect and nourish, where life, in whatever form, might arise. TOI 1785.01 is unlikely to be that world. It orbits too close to its star, baked by radiation, its surface perhaps molten rock or shrouded in thick atmosphere. But it represents hope. It represents possibility. It represents the journey. Every planet we discover expands our cosmic perspective. Every measurement refines our techniques. Every characterization brings us closer to understanding the conditions necessary for life. People ask me, will we find life in my lifetime? I don't know, but I know we're closer than we've ever been. TESS and missions like it are building the foundation. We're mapping the neighborhood, identifying candidates, developing the technology. The next generation will go further. And the generation after that might be the one that detects the first definitive biosignature. Somewhere out there, 172 light-years away, TOI 1785.01 orbits its star. Every 3.2 days, it completes another circuit, oblivious to our scrutiny, indifferent to our questions. But we are not indifferent. We watch, we measure, we wonder. TESS continues its mission, surveying the sky, discovering new worlds. Some will be confirmed and characterized. Others will remain mysteries, awaiting future technology. Each one is a piece of the story of how planetary systems form, evolve, and potentially harbor life. TOI 1785.01 might never host life. It might never be visited by human or robotic explorers, but it matters because every discovery, every measurement, every piece of data brings us closer to the moment when we find it, the next Earth, a world where life has taken hold, where biology has written its own story. That moment is coming, and when it arrives, we will look back at all the planets we studied along the way, planets like TOI 1785.01. and realize they were not detours or disappointments. They were the path. The universe is vast. The stars are many, and the search continues. If you made it all the way through this video, thank you so much. It really does mean all the world to me. Make sure to like, subscribe, and leave a comment about what exoplanet I should cover in the next video. I'll see you tomorrow, and thank you for watching.